Okay, we'll start maybe like within 1 minute. Okay, so we'll start now. Okay, so the first thing, first thing is partial derivative. So we'll start with partial derivative. So my plan is basically to revise as much as possible. Okay, so I'll try to recall the definition and we'll try to solve some problem. Okay, so that is what I wanted to do. Okay, let's see. Okay, so so am I audible?
Yes, sir.
Okay, fine, thanks. Okay. Okay, so the first thing is partial derivative. Okay, so suppose I have a map. Let's say I have a map from Rn to R. So if I have a map from Rn to R, then basically I have n variables, right? So I have n variables, x1, x2, and xn, which is an element in your domain, which is Rn. Okay, so or it's nothing like you have to always take Rn, or you can take some subset of Rn, some domain, right? So let's say F is a map from D to R. So D is a subset of Rn. So the image of x1 to xn is basically f of x1 to xn. So so basically the partial derivative of f, let's say with respect to xi, is basically it's determine the rate of change of f with respect to xi, while other constant. Yes. Variables are fixed, or you can say constant. Okay, so that is how we define, like, this is basically partial derivative. It's basically measure how the function behaves when you change xi. Okay, so and while other variables are constant. Okay, so let's say I have a map low. So okay, so let me talk about some maybe when the domain is a subset of R2 or maybe R3. So let's say I have a map in two variable. So I have a map in two variable. Right. Then the partial derivative of this function with respect to x, and at the point Okay, at the point, I'm basically giving you the definition at the point x0, x0 is, so we denote this partial derivative of this function with respect to x at this point x0 and y0 is basically limit x tends to 0, sorry, not x, it's basically h tends to 0, f of x0 y0 plus h times 1 comma 0. See, this 1 is basically saying that I'm taking this 1 0 is, it's basically the unit vector on the direction of the x-axis. So that basically saying that it's, I'm taking the partial derivative with respect to x. Okay. So right, so that this is how we define partial derivative with respect to x at a point x comma and x0 and y0. Okay, and similarly you can define the partial derivative with respect to y. Right, so this 0 1 is basically the unit vector in the direction of the y-axis. Okay, so this is how we define the partial derivative. Similarly, you can easily generalize the definition to n number of variables. Okay, so I basically I gave the definition for 2 variables. So you simply you can generalize to n number of variables. Okay, so let's say you have a function. So let's say you take a function. So let's say the function is xy by x square plus y square if x comma y is not 0 and f of xy is 0 if x comma y is 0 0. Okay, so this is my function and I want to compute the partial derivatives. Okay, so so I apply the definition. So first thing I need to partial derivative. Okay, so I have to mention the point. Okay, so I want to find the partial derivative of the function at origin. Right, I want to find the partial derivative of the function at origin. Okay, so that means the way I have defined my the partial derivative. So my x0 and y0 is basically 0 0, right? So this is my x0 and y0. Okay, this is my x0 and y0 because at 0 0 I want to compute the partial derivative. Okay, so then apply the definition. So the partial derivative of f with respect to x at 0 0 basically limit h tends to 0 f of x naught, as you can see, f of x naught and y naught plus h times 1 0. So so here my x naught and y naught is basically origin, right? So 0 comma 0 plus h times 1 comma 0. right? Minus f of 0, 0, right? So if I add these two things, then what basically I will get minus f of 0, 0, right? X, right? So now I have f of 0, 0, and the way we have defined this function gives you 0 at origin. Okay, so this is nothing but this thing is nothing but 0, and another thing is there, f of h0. So here, so certainly h is non-zero. That means h comma 0 is basically not equal to 0, 0, right? So, and again, if you go and check the definition of the function, then you can see when my point x comma y. So here in this case, my point is h comma 0, and certainly h comma 0 is not equal to 0, 0. And at that point, I define my the value of the function is basically x times y by x square plus y square. So if I plug all these values, like for this is my x and this is my y, so then what I will get basically 0, right? So then this is also 0, right? So basically 0 minus 0 by h, so I'm getting 0, right? So the partial derivative of this function, this you can say maybe some piecewise function, the partial derivative of this function with respect to x at 0 comma 0 is 0. Okay, if you directly apply this definition. Okay. And similarly, if you try to compute the partial derivative with respect to y, let's say.
Oh, so
Sorry.
So if it is 0 plus 0 by h, it will be undefined, right?
Sorry. Sorry.
So can you hear me?
Yes.
So if it's 0 minus 0 by h, it will be undefined, right?
Why? 0 by h is 0. 0, right? Because h tends to 0. See, h is coming towards 0. H is not equal to 0, right? So h tends to 0. I'm not writing that h is equals to 0. Okay, if I write h is equals to 0, then basically I'm getting 0 by 0. Right? In that case, this is undefined. But what I'm writing here, h tends to 0. Okay, h is coming towards 0. H is not equal to 0. There is a difference, right? So yeah, so in that case, it's 0, right?
Why we are taking 0, right, sir?
No, y has nothing to do with this. He's asking something about h. I'm not talking about y. Okay, certainly
No.
y is 0 here because
Yes. Yes. When we are plugging the value.
So here we have to take the unit vector in the direction of y-axis, right? So, and similarly, if you compute, what you will get, this is, if you add this, then you will get 0 comma h minus f of 0 comma 0 divided by 0. Sorry, divided by h. And as you can see, again, the same argument, h0 is basically not 0. So the way we have defined the function, if we plug the value of 0h in this expression, then you are going to get 0, right? So, and the value of the function at 0, 0 is also 0. So this is also 0. This is also 0. So eventually we are getting 0. Okay, so both the partial derivative with respect to x and with respect to y for this function is basically 0. Okay, so yeah, so this is how you can apply the partial derivative. Like you can apply this function for some you can apply this definition to this function. So, so the partial derivative with respect to x and with respect to y at origin is basically 0. So let's say, so yeah, so again, like so for few function, it's really unnecessary to compute the partial derivative by using the definition. So it can be lengthy. Okay, so for that, for example, if you have a function like this, let's say you have a function like this, please mute yourself. So suppose you have a function like this, and you want to compute the partial derivative of this function at, let's say, at point a comma b. So you want to compute the partial derivative of this function with respect to x at a comma b. So if you apply this particular definition, then it can be lengthy. Okay. So you have to compute like some cube and some product. Okay. So the best way to do, so as you know, like when I'm computing the partial derivative of this function with respect to x, then basically I'm treating y as a constant. So that means this, so in some sense I'm basically doing the single variable derivative. Okay, so I'm basically doing the single variable derivative, and in this case my y is constant. Okay, so what I can do, so first I can compute the derivative with respect to x while treating y as a constant. Okay, so if I do, then I have to apply the sum rule. Okay, so the derivative of f of x plus g of x is basically derivative of f plus derivative of g. Okay, so this is my f and this is my g. Okay, so basically the first I have to compute the derivative. Okay, sorry. So this is my s plus g. Okay, so first I have to compute the derivative of x cube, which is, which is basically 3x square. Okay, and in the second term I have 3xy, but since I'm computing the partial derivative with respect to x, I have to treat this y as a constant. So this my y is constant. Okay, so like when you compute the derivative of this function, so this is nothing but c times f dash x. Okay, so when I have to take the derivative of 3xy, then I have, this is basically 3 times derivative of 3y times derivative of x, right, which is 1. So then I will get 3y. Okay, so this is my partial derivative of this function at point x comma y, but I want to compute the partial derivative of this function at point, let's say, a comma b. So I have to plug a and b in this whatever I'm getting, I have to plug a and b. Okay, so basically if I will plug this a comma b, then what I will get, I'll get 3a square plus 3b, right? So my partial derivative of this function at a comma b is nothing but 3a square plus 3b. Okay, so for this kind of function, when your function is nice, okay, so in that case you can simply apply this the formula what you have learned in your one variable calculus. Okay.
So we can also use this method for, let's say, x a by b formula. I mean, f of x is some, yeah, as you said in the previous example. we can use that also for, I mean, this formula, we can use it for other sums also.
Yeah, here also you can use. Here also you can use, but you have to make sure that at that point this x comma y is non-zero. Okay.
U by v rule product.
Yes, you by
Sorry,
v rule.
division rule,
Okay. Quotient rule. Yeah.
quotient rule.
And similarly, you can compute the partial derivative of this function at a comma b with respect to the variable y. So when you will take the partial derivative of this function with respect to the variable y, you have to treat x as a constant. Okay. You have to treat x as a constant. So whatever this h is basically x cube. So my x cube is constant. So when I will take the derivative of a constant function, I should get 0, right? So this is my 0 plus, then I have something 3xy. So again, so in this case, I have to treat 3x as a constant, and I have to differentiate y with respect to 1. Then I will get 1, right? So this is basically 3x. And if I'll try to evaluate this function at a comma b, then what I will get? I will basically get 3. Okay. So this is the partial derivative of this function with respect to y at a comma b is basically 3a, and this is the partial derivative of this function with respect to x at a comma b. Okay. So this is the way you should try to compute the partial derivative. Okay. Not so certainly you cannot apply the trick all the time, but yeah, you certainly you can apply in the most of the time. Okay. Most of the time you can use the formula what you have read in your one variable. Okay. Basically, the main trouble is when you have some kind of piecewise function. Okay. Certainly you can apply this formula when this x comma y is non-zero, but certainly you cannot apply it when x comma y is 0. Okay. Okay, so now the next thing is directional derivative. Okay.
Sir, I have one doubt in the previous example. So that example xy by x square plus y square is answer.
Yes.
So for this function, limit will limit will exist, sir, this function.
I have already explained it, right?
Okay.
The whole process.
Okay. So okay. If limit is not existing in this one, sir, like how the
I have already explained it. Limit exists and the partial derivative is 0 basically.
Okay. Okay, sir. I'll check in the video.
Yes.
Okay.
Okay, so so the next thing is directional derivative. So the thing is why I don't want to repeat, like, because I want to like cover most of the things. So even if I'm going to repeat, then yeah. So the next thing is directional derivative. Okay. So the thing is, when I have partial derivative, what basically I'm trying to do, I'm trying to find out the rate of change of the function along the direction of this, let's say, xi axis. Okay, so when you have n variable, then you have n number of axes, this coordinate axis. So so directional derivative says, okay, so instead of computing along some coordinate axis, okay, rate of change of a function along the coordinate axis, let's say this axis, this, so here this is my x is a coordinate axis and y another coordinate. So instead of computing the rate of change of a function along the direction of x axis and y axis, we can basically compute along any direction. Okay. So along so we can compute direction of we can compute the rate of change of the function along any direction. So there is so this coordinate, so there is nothing special about this coordinate axis. Okay, we can talk about the rate of change of a function along any direction. So we can compute the rate of change of this function along this direction as well as this direction, as well as this direction, as well as this direction. So there is nothing special about this x direction and y direction. Okay, so that is, so in some sense you can say that directional derivative is basically a generalization of partial derivative. Okay. Yes, certainly the function, yeah, basically so yeah, it's not like that the function is not continuous, then see the continuity doesn't imply that so what I'm trying to say that continuity doesn't ensure partial derivative. Okay.
Limit exists, but not continuous.
No, that is what I said, like if the function is continuous, not continuous, that doesn't imply that you will always get a partial, you will not get partial derivative. Okay.
Okay.
So, okay, so suppose I have a map. So basically in your activity, you can get a lot of function where the function is not continuous, but still you have a partial derivative.
Partial derivative exists at origin.
Yes.
Yes.
So, so I have a map from Rn to Rn to R. So it's, or maybe say let's D. It's a domain. D is a subset of R. So then the directional derivative of this function, directional derivative of this function in the direction of a unit vector vector, let's say u at, let's say, a tilde a comma a2 a. So this is a unit vector. So let's say this is u1, u2, un is basically limit h tends to 0 f of a1, a2, an plus h times un minus divided by h, right? So this is how we define the directional derivative of a function in the direction of a unit vector u at this point a tilde. Okay, so this is how we define. If this limit exists, then basically this will this whatever value you will get, it will give you the directional derivative of this function at this a tilde in the direction of u. Okay, so if the limit doesn't exist, then you say that your directional derivative also doesn't exist. Okay. So as you can see, so this, let's say now my map is basically from R to R, R2 to R, and this a tilde is nothing but a comma b. And as you can see, if your unit vector u is 1, 0, then whatever this will give you the partial derivative with respect to x. Okay, if you take if you compute this, then this limit will give you the partial derivative of this function with respect to x. And when this a tilde is ab and your unit vector is, let's say, 0, 1, then whatever this limit is, it will give you the partial derivative with respect to y. And you can see, like, directional derivative are basically the generalization of partial derivative. Okay. Okay, so let me solve one problem. Okay, so let's say let's say my map. So let's say I have a function from R to R, and how we have defined this function. This function is basically x square by y divided by let's say x fourth y square if x comma y is not equal to 0, 0, right? And this is 0. Right, this is how we define the function. Okay, so I want to compute, so the thing is, I want to compute the directional derivative of f, whatever the function I define, at origin in the direction of the vector
1, 2.
Yes. So so as you can see, this this vector is basically, if you compute the norm of this vector, you will get 3 by 4 plus 1 by 4. So this is 1, right? So this is a unit vector. So then I don't have to convert this vector into a unit, right? So this is already, it's a unit. So so now if I apply the definition, what I'll get, if I apply the definition, so the directional derivative of this function at origin in the direction of this, whatever, this root 3 by 2 and 1 by 2. So this is, so here, so now if you see the definition, then basically this a tilde is basically 0, 0, and this u is root 3 by 2 1 by 2. Okay, okay, so just a minute, just a minute. Okay, so yeah, so this this u is basically root 3 by 2 and 1 by 2. Okay, so so then if I apply the definition, what I will get, so this is my a is 0, so this is 0, 0 plus h time root 3 by 2 1 by 2 minus f of 0, 0 by h, right? This is how we define the direction. So And again, I know the value of the function at 0, which is basically 0. So this one is 0. And if I try to compute this one, so this is nothing but root 3 s by 2 s by 2. Okay, so then this thing is non-zero, right? This tuple is basically non-zero, right? So in that case, I have defined in some other way. So this function is basically, so when x comma y is non-zero, the function is basically x square y by x4 plus y square. So in that case, what I will get x square, right? So then this is 3 by 4 into x square into y. What is y here? Y is let's say, so y is here s by 2. So this is basically we're getting in the numerator. How to convert a vector to unit vector? Okay, I'll come to that. So so basically, yeah, so already someone gave you the answer. So okay, so then what I have, so I have in the denominator I have x fourth plus y square. So x fourth I have 9 by 9 by 8. 9 by 8, 16, right?
Yeah.
9 by 16
H4.
4 plus y square, right? H square
By 4.
by 4, right? So so then what I will get ultimately, so this one is 0 and this one is whatever I have written. Okay, so so then if I divide the whole thing by s, then what I will get 3 by 4. Okay, let me write 3 by 8, because if I multiply 3 by 4 into half, then I'll get 3 by 8 into h cube divided by yeah, so 9 h fourth 16 plus h square by 4, right? And I have a h here. So for that I have to multiply 1 by h. So basically what I am doing here, so it's basically a by b by h, which is nothing but a by b into 1 by h. Okay. So okay, so yeah, so then what basically I can, so what I can do now, I can cancel HQ, right?
Yes.
Yes, you can cancel.
Yes. So then we have HQ. So from here, if I multiply h here, then basically what I will get 9h5 plus HQ. So I can take HQ from both denominator and numerator, and I can cancel it out. So in that case, what I will get 3 by 8 divided by 9h square by 16 plus 1 by 4, right? And as h tends to 0, this is basically 0. This tends to 0. Then eventually the limiting value will be 3 by 8, 1 by 4, right?
Yes.
Yeah, so then probably we'll get 3 by 8
3 by
into 3 by 2. Yes. So this is the final answer. So the directional derivative, whatever the function we have defined here, is basically at point origin in the direction of the unit vector root 3 by 2 and 1 by 2. It's basically 3 by 2. Okay. This is the answer. Okay, so let me quickly tell like how you can compute the unit vector. So it's basically, if I have a vector v, so the unit vector is along the direction of v is basically v by norm of v. Okay, so the norm of v, so v is what? A comma b. And what is norm of v? Norm of v is basically a square plus b square root. Okay, for example, if my vector v is, let's say, 1 comma 3, then the unit vector along the direction of v, which is, let's say, u, is basically 1 comma 3 divided by 1 square plus 3 square, which is eventually it's basically 1 by square root of 10, 3 by square root of. This is your unit vector along the direction of this p. And similarly, if you have some, let's say, it's basically I'm giving you some vector in your plane r square. So simply, if you have something in, let's say, a b c in rq, then similarly you can the same process. It's basically a comma b comma c. You divided it by norm. Okay, this one will give you the unit vector and along the direction of a b c. So the norm is a square plus b square c square. And if, okay, so let's say if your v is 1 2 1, then your u is basically v by non v. So my v is 1 2 1 divided by 1 square plus 4 plus 1. 4 plus 5 6. Okay, so this is 1 by root 6, 2 by root 6, 1 by root 6. So, and simply you can generalize to any number of, generalize to Rn. Okay, we have done it for R2 and R3. Okay, so the same way you have to take, so accordingly you have to take this norm.
Sir, in the previous question the answer is 3 by 2 and it is defined as 0, right? And the question, so therefore it is not continuous, correct?
No, it's, I'm taking the directional derivative. I'm not taking the limit. Okay, so limit and directional derivative, they're different. Okay, so I think it's not continuous, this function. Okay, certainly this is not continuous, but this is
because in particular direction, as it approaches 0 0, it became 0. It became 3 by 2.
No, actually, see, the thing is, when you are saying that I'm approaching in the direction, in some direction, actually I'm not approaching, I'm not trying to compute the limit of this function. Okay, I'm basically what I'm doing, I'm computing the limit of a different function. Okay, I'm taking a quotient. It's not, this is not my function. Okay, so directional derivative is basically, you can say, okay, so the thing is, okay, someone said like, okay, so okay, don't worry about this trigonometry thing. Okay, there is no question in your endsem from trigonometry. Okay, so
exponential questions are there.
Exponential, okay. Exponential derivative, you don't have to remember the formula, right? So the derivative of exponential is exponential. Right? So certainly that is not, yeah. So for trigonometry function, yeah, certainly you have to remember the formula. Okay, so yeah, so just you can simply ignore.
Okay.
So okay, just a minute. Let me tell what like Mohan actually asked some
Yeah,
question.
my question is that only.
So okay, that is actually a different thing. Okay, you are computing. So when I will say that, see, so for the limiting thing, if this is basically equals to f of 0, 0, then you say, certainly I will come to limit and continuity after that. Okay, then you say it is continuous. Okay, but see, so as you can see here, f of x comma y. Okay, so here actually we are taking a different thing. See here, in some sense, we are taking some kind of derivative. Okay, so partial derivative.
These two are different.
Yeah, obviously these two things are different, right? So when you see the continuity and partial derivative, they are different, right? We just like
Can also exist at partial derivative, and limit can also exist
So-
at the function.
yeah. So the thing is, so f is not continuous. That doesn't imply that f has. That doesn't imply that f has no partial derivative. Okay, so
How
even
about converse?
you are saying if f has no partial derivative, whether the function can be continuous or not.
Yeah.
Yeah, that is also possible. Okay, as far as I know, that is also possible. Okay, I have to think for that example.
Okay.
So even that is also possible. So in multivariable calculus, actually, you don't have this kind of relationship. Like no one will ensure the existence of other. Okay. Because see, there is a difference between partial derivative and derivative. I'm not computing the derivative. Actually, if you compute derivative, certainly it will ensure the existence of continuity. Okay, but the derivative and partial derivative, they are different in the sense when you have more than one variable. Okay.
Partial derivative.
So so as you can see, I'm basically computing different thing. I'm computing limit h tends to 0. I'm computing a limit of a one variable thing. Okay. So here actually I have to compute the limit of a two variable thing. Okay. So when I can show that this limit as of f of x comma y where xy tends to 0 is f of 0, 0, then I can say that f is continuous. But I am not proving anything regarding this, regarding this thing here, right? I'm completely calculating a different thing, right?
But here also H you considered both the coordinates, right? So it is directional means it is full derivative, correct?
No. Directional is not full derivative.
Partial
Okay.
derivative.
It's a partial derivative. I'm checking how the function behaves. So how the function behaves in a particular direction.
Direction.
In a particular direction. Okay. If this is my function, and when I'm computing the partial derivative with respect to x, okay, I'm basically checking how this function behaves in this direction, in this direction. Okay, I'm ignoring this direction and all other directions. Okay, so when I'm talking about partial derivative with respect to x, I'm basically checking the change of this function along this direction. So I have to only I need to check the behavior of this function over here, that whatever this image.
But in directional derivatives, we are adding to both x and y, right?
Yeah, So the thing is, when you will take some other direction, let's say u, right? So here, when you are talking about x axis, so here your y coordinate is 0, right?
Yes.
But when you take some arbitrary unit vector, okay, so when you take some arbitrary unit vector, your x and y coordinate, they can be non-zero, right?
Yeah.
So let's say this is your unit vector. Okay, so here this is my unit vector. So in that case, I will check the rate of change of this function along this unit vector. So I only have to check how the function changes along this direction. Means basically I'm checking the behavior of this function here, the whatever this region I have marked. Okay, so I'm not checking the behavior of the function along all the directions. Okay, that certainly it's basically the derivative thing, whatever, like this derivative will give you is in more or less the behavior in a neighbor. Okay.
Sir, if the function is not continuous, how can we talk about the rate of change in one particular direction? If the
Sorry?
function itself, if the function is not continuous, how can we talk about the rate of change in any particular direction?
No, you can talk about. Okay, so there are, like as I said, like in case of one variable calculus, actually, see this function continuity at a point is, you don't need, if you check, like you really don't need to talk about the rate of change of function along a direction, because you don't know like how the function behaves in this direction. So maybe if you are coming from this direction, you are getting a limit, and when you are coming from this direction, maybe your function is different, like it's quite nice in this side, okay, but it's really bad in this side. Okay, right? So in that case, you can talk about partial derivative, right? So
Sir, just to summarize, can we say that for partial derivative and directional derivative, we should not bother about continuity of the function? They can be calculated at any point.
Yes. It's as I said, like you don't have to like. Okay, so
Continuity of the function for partial and directional derivative.
Yeah, that is what I have written here, right? That is what I have written here. If f is not continuous, that doesn't imply that f has no partial derivative. Okay, so let me tell you one thing. Okay, if you want me to check your message, then send some proper message. Okay, if you want me to check, otherwise I can simply ignore your message. Okay, so don't write like anything else. Like if you have some doubt, then only you come and write in the message. Otherwise, I'll simply ignore your chat. Okay, so okay, so as I said, they are completely independent of each other. Okay, so if f has no partial derivative, that doesn't imply that also f is not continuous. Okay, so so it's more or less they are more or less independent of each other. Okay, so you don't have to, okay, once you check, okay, you check continuity of a function. If that function is not continuous, you cannot say that the function has no partial derivative. Okay, that you cannot say. And also if you check the partial derivative doesn't exist, that then you cannot say that the function is not continuous at that. Okay, so so okay, you have to check it individually. But if you have derivative, if you have the function is differentiable at that point, then basically you can say both the things exist. Okay, you have partial derivative and the function is continuous.
If it is differentiable, then it is continuous and both.
Yes. Okay, so okay, so the next thing is gradient. So so the main point of gradient is okay, so it's, you can easily compute the partial derivative. Okay, so if you have a function. Okay, someone text me something, sir. Can we take specific activity and practice questions? Krishnamon, we are taking some activity questions, right? Like, but if you want me to take some specific, then you can like that time, because I'm not going to take some 2, 3, 4 examples. Okay, hardly I will take 1 or 2 examples at max 2 examples.
Yeah, sir, even if you could take a 1 or 2 example, it will be fine. I mean, to understand the topic.
Yeah, that is what I'm doing, right?
Yes.
Yes.
There is nothing called pre-exam thing. Okay, so it's not like I'm going to I'm discussing your exam paper. Okay, so I'm going to simply discuss the concept. Okay, so yeah, so okay, so the next thing is grading. Say it's a vector. Okay, so gradient is basically it's a vector. So how you compute the gradient? Suppose you have a map. R. So then the gradient of this function at A1, let's say A tilde. Okay, A tilde is A1, A2. So the gradient of this function is basically, so you just use this notation del f. Okay, so at this point A tilde is basically you take the partial derivative of this function. The first coordinate is the partial derivative of this function f with respect to x1, and you evaluate this function at A tilde, right? And then the second component is basically the partial derivative of this function. There is x2, and you try to compute. You keep on doing. Right.
This symbol is also called nebula.
Sorry.
This symbol, inverted triangle. This
Sorry.
where you're written.
The gradient, the symbol.
Gradient symbol.
No.
Nebula.
You have some question. Okay, you can say it nebula, or maybe you can say it del. Okay, it's up to you.
Del.
Okay. Oh.
So yeah, so basically when you type in LaTeX, actually you write actually slash now. Okay, so that is how you define your gradient function. Okay, so okay, so let's say I have this function. Let's say I have this function R3 to R, and how my map is x, y, z, which is okay, I don't need coordinate, xy plus yz plus zx, right? And I want to find out the gradient of this function at point. Gradient of this function at point 1, 1, 1. Okay. Yes. Okay. So so for that, what I have to compute to compute the gradient, as you can see, I have to compute all these things. Okay, I have to compute all the partial derivatives. Okay, so so first I have to compute the partial derivative with respect to x of this function. What is that?
Y plus z.
y plus z, right?
Yeah.
And if I evaluate this one at 1, 1, 1, then what I will get? 2,
2.
right? Basically, I'm going to get 2, 2, 2. Okay, let me compute dx by dy. Then in that case, I will get x. Basically, this one will give me x. Then another one is z, right?
Z.
And
It's 2.
mm,
2.
2. Right, it will be del y. That's for del y.
del z. So okay, yeah, this one. Sorry.
This one.
Then this one will give me y plus x, right?
Yes.
That's it.
2. So then my gradient of this function at 1, 1, 1, which is nothing but
2 del by dx.
1, 1, 1. So as we have computed, this is 2, this is 2, this is 2. So all the coordinates. So my answer is 2. Okay, this is the gradient of this function. So basically to compute the gradient, you just have to compute the partial derivative, and you know how to compute the partial derivative. Okay, so it's partial derivative with respect to all the coordinates. Okay, so all the standard coordinates, you have to compute the partial derivative. And once you compute that, you know what is your gradient. That's basically you have to place all the partial, you have to put it, so you have to place all the values and you have to form a tuple. Okay, so that thing will give you the gradient. Okay, so okay, so actually to tell the gradient, how you can compute the partial derivative using gradient, I guess you need continuity. Okay, so let me okay, then let me discuss limit. Okay, so first let me discuss limit then. Then I will come to the process, like how you can compute, like you already know, like how you can compute the partial derivative along some unit vector along the direction of the unit vector using the gradient. Okay. So under certain assumption, you cannot apply it everywhere. Okay, you need some continuity assumption of the partial derivative. Okay, so before that, let me talk about limit and continuity. So I say that suppose I have a map R to R. So I say that f has a limit, has a limit L at, let's say, at some point A1, A2, Rn. If this thing x1, x2, xn approaches to L as x comma x2, xn approaches to. A1, A2, A. So I can say that f has limit L at this point, okay, at this point in your domain of this function, if the functional value approaches to L when the value in the domain approaches to the given point. Okay. Then I say that f has limit L. If I don't have such number, then I say that the limit basically doesn't exist. Okay, so so the thing is, okay, so the main problematic part in computing limit of a multivariable function is basically its direction. The how basically you can approach to this point. Okay, you have multiple direction. Okay, so the thing is, so what basically we do in the case of one variable. Okay, in the one variable, what we have, limit x tends to a is L if and only a plus is a, as well as the a minus is also a. Okay, so that is the limit is L. The limit is always L when you approach from both the direction. Okay, so you have a here when you approach both the direction. When you have one variable thing, okay, when you approach from both the direction, that is basically the left hand limit, the right hand limit. Okay, so when your domain is R, okay, when your domain is R, right? But when you have a map from R and let's say don't go to R3 or maybe R4, let's do it for R, simply R. So when your domain is R, so this is your domain. Now this is your domain. Your domain is a plane, right? Now the domain is basically a plane. Right? So in this plane, if you pick a point from here in this plane, so this xy can approach to AB from infinitely many directions. Okay, so you can approach xy can approach to AB from infinitely many directions, because you have infinitely many directions in the plane. So you can come to this in this direction, let's say in this direction, in this direction, in this direction, right? In this direction, you have bunch of directions. Okay, so you have infinitely many directions. So that is the main problematic part when you are dealing with limit in the case of more than one variable. Okay, see, in case of one variable, it's pretty easy. You have two direction, you compute the left hand limit, you compute the right hand limit. But because, and for more than one variable, then you are in trouble because you have infinitely many directions. You cannot, basically it's tricky to check the limiting value for a function of more than one variable. Okay, so and also, like, it's not like you have to come from a fixed direction. You simply, you can come like this. Okay, so you can also come like this. Okay, you can come like this to this point. It's not like that you have to come from a fixed direction to a. Okay, you have multiple ways. Okay, not multiple, is basically you have infinitely many ways to approach it. Okay, and it is possible, like, if you come from this direction, you are getting some limiting value. If you are coming from this direction, you are getting another limiting value, and when you are coming from this direction, you are getting another limiting value. So this is the case. So in case of, if you try to interpret it in the case of one variable, then basically what basically in the case of one variable, you can say that the left hand limit is basically not equal to right hand limit. Okay, since in the case of one variable we have only two different directions, so that's why we get left hand limit is right hand limit. But here you have multiple directions, so it can happen if you are coming from two different directions, and you can get different limiting values. Okay, so in that case you say that the limit basically doesn't exist. Okay. Okay, so let's try to compute. Let's say I have is there any example I have given? Okay, let's say this one, right? Let's say this is my function. Okay, I want to compute the limit. Okay. This one is x square y
x4 plus y square.
y square. This is 0. Please mute yourself. Okay, so yeah, so suppose you take this path. Suppose so here I want to check the continuity of this function at 0, 0. Okay, so this is my domain. I want to compute the limit of this function, whether I want to know whether limit exists at 0, 0 or not. Okay, so let's say I'm coming along this straight line, y equal to mx, right? So in that case, what I'll get limit. So x tends to 0 because y equal to mx. So y equal to mx. So if y equal to mx, then xy tends to 0, 0 is basically equivalent to x tends to 0. So then x cube into mx divided by x fourth mx, right? Mx m square x square. So then this is mx cube divided by x fourth m square x square. Now if I cancel x, then what I'll get?
X square common mx by x square plus m. X square plus m square.
X square
Plus m
m square. Okay, so then what will be the limit of this function?
0.
0.
0,
0. Why?
X is 0.
0.
Numerator is
0
0.
by m square it will be. So
You have x square here, right?
Top numerator becomes 0.
numerator becomes 0, denominator is m square.
No, I still no, I'm not sure. Like, what is the limit of this function? Limit
0, sir. Numerator will become 0.
mx by x square. What is the limit of this function?
This is
Undefined.
This is undefined.
Undefined.
But you have a denominator m square, right? Plus m square.
plus m square is there.
Okay, correct. So limit x tends to 0. So this is basically converging to 0. And this one is converging towards m square. Okay, so that's why we'll get 0, right? So basically what this limit is saying, when you are coming along any straight line, you are getting your limit at 0, right?
Yes.
But as I said, this will not ensure that the limit of this function is 0. Okay, because what we are computing the limit along the straight lines. So, okay, when we are coming to this AB through straight line, in that case, I'm saying my limiting value is 0. But I'm missing all these things. Okay, so this type of things I have missed this type of curves. Okay, so let's say now you take, so instead of coming along a straight line, you try to take this path, y equal to
X square.
mx square, right? You try to compute y equal to mx square. So then similarly you take limit x tends to 0, x square into mx square, okay, divided by
X power 4. M square x power 4.
So in this case, your limit is m by, right? So if you take m to be 0, then you are getting 0. When you are taking m equal to 1, you are getting 2.
1 by 2.
When m equal to 2, you are getting 2 by 5.
2 by 5.
Okay. So for different values of f, you are getting different limits, right? So basically, for when you are coming to this origin along this curve, okay, for different values of n, you are getting your different limit. Okay, so in that case, you can say that the limit doesn't exist. Okay, so that is how you. So as I said, it's tricky. Okay, so computing limit in the case of more than one variable, it's tricky because you don't have any control on the path that you can take to compute the limits. Okay, in case of one variable, you have that control. Okay, you know I have only two direction. Either I can come from the left or I can come from the right. But you don't have that kind of control when you are computing for computing limit of a function of more than one thing. Okay.
But earlier it was mentioned, it was committed that if the power of the numerator is less than the power of the.
That is actually, yeah, this is not like you have to prove it. Actually, it's I don't think it's true in general. Okay.
Okay. What was the comment actually?
Yeah, so basically, if the degree of this one, whatever, like this in the function which is in the numerator is greater than the degree of the function in the denominator, then most likely you will get a limit.
Limit. Okay.
Yes. But when you have the equality, or maybe this one is the degree of this function in the denominator is less than the degree of the function in the numerator, then mostly you will not get a limit. Okay. So as I said, in most of the cases you will get if you apply, then you will get the result. But there can be few
greater. Degree of numerator must be greater.
Yes. But some cases you may get something wrong. Okay, but in the most of the cases you will.
So how the degree plays in this new calculating limit?
Okay, like I am not going to discuss all these things. Okay, because these are basically, yeah, so not yeah, so there is no verified proof for all these things, and yeah, so that's why we're not going to. It's basically, it's yeah, but
So,
okay,
but how we get
we are
that?
not we are not discussing this parametric thing in our course. Okay, this x cos theta and y, x is equal to r cos theta, y equal to r sin theta. Okay, so yeah, so the thing is, this is, take it as a fact, or you simply you can ignore it. Okay.
Okay.
Okay, so if you want to take it as a fact, or simply you can ignore it. As I said, if this is not true in general, okay, it will happen in the most of the cases. So simply you cannot go and apply to any function, and you cannot claim that you will get the result.
Okay, we can ignore that also, right?
Sorry?
We can ignore that also, right?
Yeah,
I mean,
if you want, you can ignore that. Okay, as I said, this is not something true in general. Okay.
So the proper way of doing it will be substituting y equal to mx or some curve.
For this course, actually, we are doing in this way, but this is not the only way to check all these things. Okay, for this course, we are doing in this way. Okay. Ajay, someone already mentioned you have something called parametric thing. Okay, that is also a one method. Again, that is also not a foolproof method. Like you cannot say that, okay, I apply parametric, then I will get the limit. That is also not okay. That is also a similar kind of method. Okay. So not similar, it's slightly different, but again, that is also not like, as I said, it's not like the foolproof thing. Okay, if you apply that one to some function, then it's not like that ultimately you will get the limit. Okay, so next thing is continuity. Okay, so
Sir, is it possible, like, can you explain the sandwich theorem? And
sorry,
you
sorry.
can explain the sandwich theorem also? Sandwich theorem.
Yeah, I'll come to that.
Yeah,
I'll
yeah.
come to that. Okay, so because see, to prove sandwich theorem, I have to prove that limit exists, right? Okay, so
Yes, sir. That's
I
correct.
cannot apply sandwich theorem to each and everything. Okay, so I have to apply to some function. Okay, so
Okay, sir.
maybe
Sure.
I will take some function where I can actually really I can apply this sandwich theorem. Okay, because yeah, certainly I cannot apply it
Sir, please
everywhere.
mute all.
Action will be taken against you. You
Okay.
understood now?
Uh, yeah, so the thing is, who is Asutosh? Hello? Okay, so Asutosh, please don't do it again, otherwise I'll remove you from the
Yes,
session.
you. I'm watching you.
Okay, so yeah, so the thing is, okay, let me take some function where actually I can apply this sandwich theorem. So you have some kind of example in your assignment. Just give me a minute. Hello.
yes.
No, you cannot apply for L hospital rule for a function of two variable. You have to convert in into a function of one variable, then you can apply it. Okay, you don't have some kind of L hospital rule. Like
So we
there
don't
is
use
one,
it
but
for,
it's a slightly complicated. Okay.
so we don't use for two variables, right?
No,
As
you
opposite.
cannot use it for the two variable. Okay, so if it's continuous at a point a comma b, if basically if the limit is same as the functional value, okay, whatever limit you will get at that point, if that is the same definition that you have seen in the case of one variable, if the limiting value is same as your functional value, then you say that your function is continuous. Okay, so no, the thing is I'm searching that problem where actually you can apply. Okay, so as far as I remember, this is something like this. Okay, so generally you take this function So this is my function x square times y square divided by x square plus y square. If 0 and it's 0, if your x comma y is 0, 0. Okay. So I want to check whether this function is continuous or not. Okay. So so the thing is, okay, if you as I said again, taking limit of more than one variable function is tricky. So if you take this line y equal to mx, and if you compute, then what you will get? You will get m square x fourth by x square plus mx square. So eventually you will get 0. Okay. So the thing is, again, if you take
Those
some,
are
sorry,
yes, 0, 0. Yeah.
0, yeah.
With m square x square.
भेजी थी मैंने, उसमें रखा है, मेरा एक मीटिंग चल रहा है.
Okay, again, say that, like, yeah. So better if you mute yourself. So if you take m square, let's say y equal to m square. Okay. So
will be m square x square.
can you say it loudly?
So in the denominator, I think it will be m square x square.
So you are talking about this one, this one.
Yes, sir.
No, like see, this is
If you
what.
take mx, then it should be m.
Yes, sir. Yes, sir. M square x square. I think.
Square,
We
square,
are
x
replacing
Sir, it's y
Okay,
square, no? It will be
okay,
m square
okay,
x
this
square.
one. Okay, this one is m square x square. Yeah, true. So eventually, if it is m square or m4, eventually you are going to get 0, right?
Yes, 0.
Yeah. So okay. So yeah, sorry. So the yes, it should be m square. So then okay, if you take some path, let's say y equal to mx square. Okay. So then what you will get? You will get x square plus m square x fourth, right?
Yeah.
Divided by x square plus m square x fourth, and you can check that this is also 0. So why actually, ultimately, if you are going to take any path, you are going to get 0, only because this function is continuous. Okay, but certainly if I take some 10 different paths and I show that the limit is 0, that certainly is not a valid proof that this function has a limit. Okay, you have to prove it mathematically. Okay, this has a limit for it doesn't matter what kind of path you are taking, ultimately you are going to get 0. Okay, that you have to show. If I'll take some n number of things, let's say now I'll take some mx7, or maybe if I take x equal to my square, and in all the cases, if I'll show that the limit is 0, then certainly it's not a proof of the fact that this function has limit 0 at 0. Okay. It's not a proof. You have to prove it thoroughly, like, because when I'm taking all these things, actually I'm showing that limit is 0 for all these paths. Okay, but still I missed infinitely many paths. Okay, so in at least in this course, to solve this kind of thing, when the function is continuous, basically we are using some kind of like, as I said, as someone already mentioned, we are using this sandwich lemma. Okay, so basically how we can check how we can apply this sandwich lemma over here. So you have x square here, and you have this one x square plus y square here in the denominator. So as you can see, your x square is less than, right? So then you can divide it by x square plus y square. So what you will get? 0 by but I want to apply Sandwich lemma in to f of x. I want f of x here, right? I want f of x here. So still I don't have f of x here because I'm missing this term. Still I don't have y square here. So for that, what I have to do, I have to multiply y square. If I multiply y square, what I will get? So now you apply the limit. Now I don't care what this limit is, but I don't care what this limit is because if I can compute this and I can compute this one and I can show whether if they are equal, then basically I can say that this limit is also whatever limit I'm getting on the left and on the right. Okay, so that is basically the advantage of Sandwich lemma. And you can see this is a zero function, so the limit is 0. And this is limit, basically this is equivalent to find the limit of y square as y tends to 0. Okay, so this is also 0. So this is 0 and this is 0. So eventually this limit is 0. So now actually we basically showed this limit is 0. It doesn't matter what path you are taking. It's basically we are giving a proof that whatever may be the path, we are always going to get 0 as the limit of the function at 0, 0. Okay, so the limit of this function, so limit
and it is continuous also, right?
Yeah, it's basically continuous. It's basically 0. Now to say whether this function is continuous or not, we have to check whether this limiting value is equals to f of 0 or 0 not, because f of 0, 0 or not, because we are computing the limit at 0, 0. Okay, so to say this function is continuous at 0, we just have to check whether this limiting value is equals to f of 0 or not. Okay, and as if you go and check the definition, we have defined it like this. Okay. So then this is f of 0. That means f is continuous. And if I simply change this function, like if I define at 0, 0, if I define f of x, xy is as 1, then I have 0 here, but I have 1 here. Okay, so I don't have equality. In that case, f is not continuous.
The limit exists, but function is not continuous.
Yes. Okay, so that is basically more or less, you may have heard about this term, removal continuity. Okay, so
F00 value is coming 1, right?
yes. Okay, so the next thing is okay, I have discussed something about gradient.
Here F00 we have to compute, or it is because
it is given. It is given. So in the actually in the beginning I defined f00 as 0. Okay, so in that case f of 00 is basically the limiting value, right?
Yes.
So that's why f is continuous. But in the second case, what I did, I changed the value. Okay, so if I take instead of 0, if I define this as 1, so in that case I don't have equality, right?
Yes.
So in that case my function is not continuous. So I basically I simply changed that value of the function at 0 points.
Oh, so
Hmm.
so can you just explain one question from activity 9?
That is the question. Whatever I explained here is basically from activity.
So, but this one has it. It didn't have like constant values on its power. So that
Yeah. So I'll try to explain it in the end. Okay. If I'll get like, see, the thing is yeah, I don't have any problem of explaining taking activity question, because if I'll start doing this, then I cannot reach till week maybe say 11. Okay, that is not possible. I have to stop somewhere in between week 10. Okay.
Okay. So can we do it at the end?
Yeah.
Okay.
Certainly the session will go up to maybe 3.5 hours, or maybe I don't know. After that, I am not sure whether I can take your question. Okay, so in that case, if it's not continuous. Okay. Okay, so the next, okay, so we have discussed something about gradient. We have defined what is gradient, and I wanted to tell that so here we have defined gradient. So to compute that, so if I know gradient, actually then I can easily compute the directional derivative. Okay, I don't have to compute. I don't have to do all these things. Okay. I don't have to take the limit, and I don't have to compute the limiting value. So once I know the gradient, then simply I can compute the directional derivative. And that the problem is you cannot apply that method everywhere. Okay. If the function satisfies some condition, then only you can apply that method. You cannot apply it everywhere. Okay. So the thing is, suppose it's a map from Rn to R. So the condition is basically, when you can apply that method, the condition is if the gradient exists, if the gradient exists, and so I want to find the directional derivative of this function at some point A, and in the direction of u. Okay, in the direction of some unit vector u. So to apply that gradient method, you need one condition, and that condition is that this gradient should exist, and it should be continuous on some open bulb around this point, the point 8 theta. Okay, if this condition holds, then the directional derivative of this function at A tilde in the direction of u, that is how we denote directional derivatives. So this is directional derivative of f at A tilde in the direction of u is nothing but the gradient of this function at A tilde dot product with u. So this is basically a n tuple, right? This is a n tuple. So this is a n tuple, and we are taking a dot product with some another type tuple. Okay. Ultimately, you will get some scalar. So this dot product makes sense. Okay.
I have a query here, sir.
Yes.
So while trying to calculate the directional derivative So here, if the requirement is it should be defined, well defined in the open code, right? Now, if it doesn't happen, if there's no continuity, then the only option is again we have to go back to the earlier formula. Right?
Yes.
F of 18 plus HU, all those things minus F of 18 by.
Exactly. Yeah. Then
That's the only way out, right?
Yeah,
If
that
we-
is the yeah.
Oh.
If this thing is, if this condition is certainly not true, then you have to go back to your main formula and you have to apply it using your normal method. Okay, you cannot apply this trick here.
So because when you're trying with the other one, sometimes we're getting stuck with, like, in the sense simplification is getting into a problem because the denominator h is not getting eliminated.
Yeah. So for function like this, okay. So for function like this piecewise function, mostly most of the time you cannot apply it. Apply this formula at 0, 0. Okay, so for if like for nice function, so for some nice function like polynomial or maybe let's say some kind of sin x or maybe cos x or maybe exponential function, you actually you can apply this thing because they are actually nice function. It's not like they have continuous partial derivative. Okay, yeah. So even they are like infinitely time, they are C infinity function in some sense. Okay.
Sir, here we are basically finding the direction, a derivative, partial derivative, that is a gradient along standard direction, and taking a projection along that wanted direction, sort of. That is the unit vector u. Is it?
Sorry?
We are basically taking the projection of the gradient vector along the unit vector u.
No, projection. If you take some projection, then you will get a vector. So here you will get.
This is dot product is giving that only, no, sir? We are
no. Dot product won't give you the
scalar. It is giving a scalar.
Scalar. Okay. So if you are going to take projection like in R2, then you will get some vector in R2, right? So
okay.
So but here you are getting scalar.
Okay. Understood. So, thank you,
yeah,
sir.
Yeah, thanks.
Sir, here
multiply this with the unit vector,
then if you have some kind of similarity in your projection formula. So basically if you take some multiply with whatever scalar you will get, if you multiply with u, then you will get the projection.
Okay.
But here you are basically taking the scalar.
Sir, here inner product is defined as dot product, sir.
Yeah. So when we're doing multivariable calculus, like all your inner product are basically okay, because here actually we're taking this coordinate axis as your standard basis. Not standard, yeah, they are basically the standard coordinate we're taking. So when we're doing multivariable calculus, all our inner product are basically your dot product. Yeah, so you have to remember that in the case of multivariable, not in general. Okay, so for example, let's say this is my function. Let's say my function is, I'm taking some nice function, let's say x square plus y square, and I want to compute the directional derivative of this function at 1, 1 along the direction of let's say 3, 4. Okay, so this is certainly not a unit vector, right? Because if you compute the norm, this is basically 5, right?
Yeah.
So then we have to divide this vector by its norm. Okay, so if we'll do that, then our unit vector is 3 by 5 and 4 by 5. So, so now I have to compute the gradient. The gradient is basically what?
2x,
2x,
2y.
2y. Okay, so 2x and 2y actually they are continuous function. Okay, they are polynomial function. Okay, so I'm done with this condition because this condition is certainly true for this tail length. Okay, so 2x, 2y they are continuous everywhere. Okay, so my gradient function is continuous.
How will you check this?
Sorry.
How will you check this continuous? Like
No,
2x?
polynomial function they are continuous, right? You can check it. Okay, there is a proof to check whether a polynomial function is continuous or not. Okay, that is certainly not difficult. That the way you check for one variable calculus is basically the same. Okay. So, so this is continuous on R square. That means certainly it's continuous. That means certainly it's continuous on open ball around 1,1. Okay, so once my condition, once this condition holds, then I can apply my formula. Okay, so then the directional derivative of this function along this direction at 1,1 is basically what? Del f, which is 1,1 1,1 times 3 by 5 4 by 5. Okay, so in that case this is 2 times 3 by 5 4 by 5, and in this case it's 6 by 5
14 by 5.
Yeah,
8 by 5.
8 by 5. Okay, so as I already mentioned, you don't have to compute limit. It's simple. You compute no, you cannot apply. If the gradient doesn't exist, then certainly you cannot apply. Okay, you need something more than the existence of the gradient. The gradient should also continuous. Okay, so it's even if the gradient also exists, also you simply cannot apply that formula. You have to make sure that your gradient is also continuous. So only existence is not enough. Okay, so certainly your gradient doesn't exist, then it's pretty obvious that you cannot apply.
Sir, does it mean that we are trying to compute gradient and then find its component along the given?
It's no, we are not trying to find the component. As I said, it's component. When you take a component, you will get some vector. Here we are getting the scalar. Okay, so
the magnitude of that component.
Which component?
No, because see, it looks as if, I mean, I'm not a mathematics expert, but it looks as if we find the directional derivative, that is a gradient, along a convenient standard direction, and then we try to relate it to the direction in which we want to find the directional derivative. So we take a dot product and we say that now this is the directional derivative. So it is some sort of a mathematical trick rather than going to the original formula of finding it from the basic definition. What we do is that we are finding the gradient along a convenient standard direction.
Yes, true.
And then we say that, okay, now take a dot product with that.
Yeah. So more or less, yeah, you can say that more or less actually we are trying to find the rate of change of the function in all the direction. Then basically we are taking the dot product.
Okay, sir. Thank you.
Yeah. Okay, so yeah, so you can check like this is 2x 2y, and if you compute 2x at 1,1, then you will get 2. If you take 2y, if you evaluate 2y at 1,1, you will get 2. Okay, so that is what we are getting, 2,2 dot product with the unit. Okay, so yeah, so again, next thing, yeah, so I'm done with this week 9. Yeah. So again, I'm trying to emphasize on this fact that you cannot apply this thing to all the functions. Okay, you sometimes you can get some function where this derivative exists, but it's not continuous around that point. Okay, so in that case you cannot apply this rule. Okay.
So for what kind of function derivative does not exist? Gradient?
No, the gradient exists, but it's not continuous.
Is there some case where it will not exist? Which
See, the thing is, if one of the partial derivative doesn't exist, then your gradient doesn't exist, right? What do you mean by gradient exist?
does not exist means it becomes zero. Zero also it exists. Right?
No. Zero means it exists. Okay. It doesn't exist means the limit has no value. Okay.
Undefined or something.
Basically, the limit
1 by 0.
Basically, the limit doesn't exist. Okay.
Sure, in that case, you have to use the original formula, right?
Yes. Okay.
So in that case, can you use this L'Hopital rule? I mean, if the limit is not existing, I mean.
L'Hopital rule you cannot apply everywhere to find the limit, right?
Okay.
So certainly then you cannot apply it. It's depend on the situation. Okay, so you cannot apply like blindly. You cannot apply L'Hopital rule everywhere. Okay, if you have some kind of situation where you can apply, then you should apply that. Okay, it's not an issue. And again, you must have a function of one variable. Okay, there is no such like some kind of trivial way to apply L'Hopital rule for a function of two variables. Okay. Okay, so the next thing is so the next thing is, I guess, what is there? 10. Yeah, equation of tangent line. Okay. Okay, so this whatever is there in week 10 is basically it's related to the things. Once you know how to compute directional derivative then and gradient, then these are actually basically there is nothing. It's not difficult to find this tangent plane and tangent line. Okay, so this is more or less related to finding your directional derivative, and for tangent line you need to find the directional derivative, and for tangent plane you need to find the gradient. So once you know how to find the gradient and directional derivative, then basically yeah, so you can find the tangent line and as well as the tangent plane. So so suppose let's say I have a map from R2 to R. Okay, so I have a map from R2 to R. So, so then the equation of the tangent line, at let's say point A comma B in the direction of a unit vector 2 is basically this. I'm basically giving this parametric form of the line. So this is basically a plus t times u1. So I'm taking the first coordinate of this point where I'm trying to find the tangent line. So I'm trying to find the tangent line at this point. Okay. So if I take the graph of this function, so then basically what I'm doing, I'm computing the value of the function. So this point is basically what? A, B, f of a. Okay. So when I'm trying to find the tangent line in this direction, then more or less I will get this line. Okay. More or less I will get this line. This is basically the tangent line along this direction. So this is t e1, yt is b plus t u2, and zt is what? Zt is f of a comma b plus t times f of u a comma. So this is basically, this is directional derivative.
It is a gradient vector into the unit vector.
Yeah, so this is basically, no, this is basically the directional derivative of f at a comma b in the direction of.
So that is the dot product of gradient vector and the unit vector, right?
That certainly you can say if your partial derivative is continuous, right? Yeah. Otherwise you cannot simply, you cannot write it like this, right? You simply, you cannot write it del f.
Okay, it is continuous.
Yeah, a comma b dot t. Certainly you cannot write. If the partial derivative is not continuous, then you cannot apply it, right?
Okay.
So yeah, so if that is the case, then certainly you can apply it. Okay.
If the partial derivatives are continuous, then these all tangent lines will lie in a single plane, right? But if they are not continuous, then these lines will not lie in a single plane.
Yes, true. Yeah, if all the partial derivatives are actually continuous, then if you take all the tangent lines in any, like if you take the tangent lines at all tangent lines at AB along all the direction, they basically they will lie in a same plane. Correct. Okay, so this is how.
So one small doubt, sir. So this xt, right? You mentioned as a xt. So can you just, okay, A, I understood this is a parameter. Okay. Plus, then what is this value, sir? Is it t something? Or t or what? Like I didn't get it actually, sir.
This is, sorry, yeah, this is t.
T. So what does it mean, sir? T? What is
T is basically, it's a real number. Like it varies over reals. Okay.
Okay, this is some real number, some constant will be there.
Yeah, see, this is basically, it's a, see what actually we are doing. Okay, so okay, let me right.
Sir, is this a real number or a scalar one?
So okay, I don't know what is the difference. Okay, so whatever you are said, like it is a real number or it's a scalar.
It's a scalar. It's a kind of scalar only, sir. I understand.
So what basically we are doing? So this is basically what this parametric thing. What we are taking u1, u2, right? Yes, so this is t times this, right?
Yeah.
So where t.
So where is AB and f of AB. That is
yeah, I'll come to that. I'll come to that. Okay. So basically, so this is basically in the span of a point, right? This is the span of this point, right?
correct. Yes.
So basically what you will get, it's a line. So basically,
So
it's
is it because to show that that line is not passing through origin, then the distance, is it for that?
Sorry.
Like the affine space thing, the distance from the origin kind of thing?
No, certainly it's a line, then certainly it's a affine, certainly then it is a affine space, but I still don't understand your second line. Like,
see, meaning basically, generally when we give y equal to mx plus c, we generally give the line, equation of line, but over here, if the line is parallel to the, or the plane or line is parallel to the line or plane passing through the origin, is it for that purpose? It is that it indicates that t into something.
no, this is basically, it's a line which passes through this a comma b comma c, f of ab. That is what actually I want to show.
Okay.
It is a line passing through that.
Yeah.
Okay.
So basically, I'm trying to tell like what basically this parametric form is. So there is a t here, right? You have a t here, you have a t here, you have a t here. Right? Yeah. So if I try to write this in some component form, so it's basically t into u1, u2. So then it's a line, right? It's a line which passes through origin and as well as this point u1, u2. So it's a line which basically passes through this thing. Okay. So after that, what actually I'm doing, I'm adding a comma b comma f of a. Okay.
Here the unit vector is u1, u2, u3, right?
Yes.
Which we have considered.
It's not unit vector. Okay. So because you have f of u a comma b.
When we say in the direction of u, it means we will consider u1, u2, u3, right?
Yeah, see, this is certainly this line is along the direction of u1, u2, f of u comma ap. Okay, but still we don't know whether this is a unit vector in R3 or not. Okay, certainly if you project it on the xy plane, what you will get? u1, u2, 0. We know that this is certainly a unit. Okay.
Okay, so to match the coordinates where we want to get our tangent, we are shifting the axis, right? We're doing this affine transformation.
No, the thing is, yeah, so basically this whatever this parametric, it's basically it represent the tangent line at point a comma b, right? So the line should passes through this point, right? A, B, f of a, b. That is what actually I'm trying to show. So, okay. So if I add with, let's say, a comma b comma c, let's say this is my point a, b, f of a, b. So if I add this one, so if I take this one, a, b, f of a, b, then basically I'll get a line passes through a, b, f of a, b, and which is basically this line is basically parallel to. Okay, maybe I slightly, yeah. So
it will be parallel.
Yeah. So let's say this is like this. This line is basically parallel to this one. Okay. So this whatever I have written here, it's basically this line. Okay, it's a line passing through A comma B comma C and along the direction of U1, U2, F, the directional derivative of AB in the direction of. Okay, so that is, so this line, whatever this line is, passes through this and it's along the direction of this vector. Okay.
We got the parametric thing. Then we have the equation also, right?
Sorry.
We have the parameters for x, y, and z. And based on this, you have to find the equation.
Yes, yes.
Plane.
Yes. So, okay, so and also like you have something called symmetric form. Yes. I'm going to take example. Okay. So you
This
have
tangent line is not unique, right? There are many tangents on the single point.
Tangent line, you are saying?
Yeah.
Tangent line, see, certainly tangent line exists, then it is unique. Okay. But as you see, the thing is I can change this direction, right?
Okay.
So if I change the direction, then I may get a different tangent line. But for a fixed direction, okay, the tangent line is unique. Okay.
Right.
Because I have this control of this on this direction, right? So here I am taking this along this direction, some in the direction of E1 and D. Okay, so but I can take some different direction, right? My unit vector can be something different. So in that case, I may end up with some different tangent line. So this is basically the parameter symmetric form, symmetric equation, and the vector form is
what you wrote earlier.
Yeah. So basically, you can. It's basically I'm writing in sort of this vector form. Yeah. So whatever I have written here, this one plus this one.
Sir, where we are supposed to use the symmetric equation form, like scenario?
Not scenario, it's a different way to represent the same thing. Okay, it's not something, it's a different form. I'm writing the same thing in some different form. Okay, and they have some name. No, you don't have, really you don't have to remember all the three forms. Okay, once you know this one, then you can actually check what is your answer. Okay, because they are the same thing. It's what actually I'm doing here. It's basically you have xt is basically a plus t e1. What actually I'm doing?
T is missing.
T is x minus a by e1. Okay, so once you know this, once you remember, like not remember, yeah, it's basically it's if you know the idea, like what actually you are doing. Okay, then also you don't have to remember this. Okay, it's basically it's a tangent line in the direction of this e1 e2 and its gradient. And this one is what is that? F of AB
fu of
plus t into
plus
t
t into u1 plus u1 into fu of db.
So yeah, so the thing is, once you know this, okay, so the rest thing they are basically same. Okay, so eventually you can compute like which if you have some symmetric form or maybe vector form, you can easily you can check whether that thing is equals to this equation or not. Okay, so let me take a question. So let's say this is my function. And I want to compute the equation of the tangent line. At 1, 2 along direction of 1, 1, right?
Okay.
So if I go and check the definition, so this is my AB is 1, 2. And as you can see, this is not a unit vector, right? So then I have to convert this one to some unit vector. Okay, so so if I do it, then my unit vector u is basically what? 1 by root 2. 1 by root 2. So okay, so yeah, so I want to compute the equation of the tangent at point 1, 2 along the direction of this 1 by root 2 and 1 by root 2. Then okay, so then I have this thing, this formula.
You will use the symmetric equation or the parametric?
You can use anything, like whatever you want. Okay, so let me do it for see this writing this parametric thing is slightly easy. Not parametric, yeah. So writing this parametric equation is slightly easier. Like
then you have to convert to the equation, right? For
see, like
if the question is equation of the line means we should get a equation form. Correct?
Yeah. Then if in your option you have only symmetric form, okay, then you have to compute the symmetric form. Okay, see, as I already said, once you have parametric thing, okay, it's not difficult. It's not that difficult. You can, once you know how to compute the parametric thing, then certainly you can compute the symmetric form, right? And also once you know how to compute this parametric thing, you can also compute this vector form.
Okay.
So computing one is enough. Okay, from after once you compute one, then actually by looking at the option you can say which one is correct. Okay, so okay, so the first thing is x comma t. What is that? It's basically by our notation, it's a plus t times u1, right?
Yeah.
So this is a is what? 1
plus t by root 2.
T by root 2. Then similarly yt is what? B plus
2 plus
t u2. Okay, so this is u1, this is u2. So b is 2 plus t root 2. Okay. So the next thing is what?
F of AB.
This whatever this
ZT.
ZT. It's basically f of AB
Plus T times
the
FU
directional derivative of f at AB in the direction of u. Okay, so what is f of a comma b? 5. Yeah. And what is the directional derivative of this function along
2x 2y.
Yes. 3 root t 2x 2y. We have to substitute 1 comma 2, which is
2 2
2 4. 1 comma 2.
At okay.
Right. We have to substitute. We have to find the at a comma b and times u. Right? So then you have dot product with 1 by root 2. 1 by root 2, right?
Yes.
So then we have basically 6 by root 2, right?
Yes.
So you can simplify this. Okay, so it's 6 by root 2. So then basically this is your equation of the tangent plane.
Good. Equation form is not there, right?
Sorry.
Line should have an equation, right? Y equal to mx plus c, something like that. It doesn't come in that form.
No. See, that is actually, you have that kind of thing in the case of one variable. Like in R square, actually you can represent like this. In actually the problem in R2, you cannot write it in the form of some y equal to m. So, or maybe x plus by plus c cz. You cannot represent. That is basically equation of the plane. Okay.
Yeah. Okay. So any line in R3 is only in parametric form.
Yeah. So even in R3, even in R4 also you cannot do the same. Okay. So basically when you write something actually what, like I say some x plus by plus cz, then it's basically it's basically a hyperplane. So in the sense, hyperplane is basically it's a plane with dimension the dimension of this plane is less than less than 1 of your whole space. Okay, like if see this, what is the dimension of this one? It's 2, right?
2. Yeah.
And you are representing it in R3.
Yeah.
Okay, so it's
therefore it is called hyperplane.
Yeah. That is why it's called
all
hyperplane.
planes are only 2, right?
Sorry?
All planes will have dimension.
No, all planes have it's depend how you are using the word plane. Okay, if you are using like in R3, then it's basically plane. Some people they even use the word like for they say it plane even for this one also, like CZ plus A B C D D dot. They also use plane for this one. So you have to choose it accordingly, like when you are using that word plane. Okay, so this is
in R3 all planes and all hyperplanes are same.
Yeah, you can say that. If you are saying that your plane is basically two-dimensional object. Okay, when you are saying your plane is two-dimensional object, then you can say that okay, you are in R3 only your plane and hyperplane are same. Okay, but as I said, in many places they use plane even for a three-dimensional thing, or even for four-dimensional thing.
In two-dimensional, you don't call it hyperplane because it is the full space, full dimension.
No, hyperplane is basically it's a plane. It's if the dimension is just less than 1 of your whole space, then you call it as a hyperplane. That's all. Okay, but as I said, like, see, since you are saying that you are only using the word plane. Okay, the word plane for a two-dimensional thing. That's why you are saying, okay, in R3, actually your plane and hyperplane, they are same. Okay, but as I said, this is not like some universal what terminology. Okay, some people, they use the word plane for this one. Okay.
This is dimension is 4 or dimension is 3?
This is dimension is 3. Oh.
Okay. What is dw? Constant.
No, d is constant, w is variable. Oh.
Okay.
Fourth dimension.
It's a 4-dimensional object. Oh.
So a 4-dimensional means then it is not hyperplane because the plane will be 2 less, right?
No, this
plane is 4.
This dimension of this plane is 3, right?
Oh.
See, this plane is in R4. But the dimension of this plane is 3, right?
Difficult for us me to.
No, it's not difficult. Okay, so
one can be expressed in terms of other three.
This is W.
Sir.
Okay, this is a subset of R4, right? X, Y, Z, W, right?
Yeah.
So where all of them are elements of R. So this is a subspace of R4, right? So the dimension of R4 is 4, right? But here actually.
But why is that with 4 variables? Plane will have only 2 variables.
This is, as I said, you can use the word hyperplane.
Sir, here we are talking about plane. We are meaning collection of tangents in all directions. Right?
No, I'm just talking about plane. That's all. I'm not talking about tangent and all these things. Okay, I'm just saying the plane. Okay, see, if the dimension of the plane is just less than like less than 1 less than your the dimension of the whole space, then you call it as hyperplane. Okay, so as you can see, like you can write this variable w in terms of x and y and z. Okay, so that's why you have the dimension of this one is basically 3.
Okay.
So here you have 3 independent variable, right? Yeah, so that's why the dimension is basically 3. Okay, so you can ignore all these things. So it's not required for your exam. Okay, so this concept of what is the definition of hyperplane and all this thing. So okay, so this is how you compute your equation of your tangent line. Okay, so the next thing I want to do, again, if I'll get enough time, then I'll try to do more examples. But yeah, the thing is, so as you can see, if you know how to compute this one, okay, because this is the only non-trivial thing you are doing. Okay, you are computing the directional, but if you know how to compute this, then basically you are done. So the next thing is, and you can see that if this directional derivative doesn't exist at that point, then certainly you don't have a tangent plane. If this directional derivative doesn't exist at that point, then certainly you don't have tangent. Okay, at that.
There is no tangent.
Yes. Tangent, not tangent plane. Then you don't have tangent line. Sorry.
Yeah.
You don't have tangent. So you to talk about tangent line, you need at least this existence of this so-called this directional derivative. So tangent plane of a function. let's say again I'm taking some function from R to R. Okay, I'm not going to R3. Okay, so let's say I want to again I want to talk about some tangent plane. So let's say this is my graph of this function, and I want to talk about this is my domain. This xy plane is my domain. So I'm taking some point a comma b in my domain. Okay, then if I draw the graph, I will get some somewhere here. So take it as a b g. So if I draw, then I'll get the image. Okay, so I'll get the height by this number f of a comma b. Okay, so I want to talk about the tangent plane of this function at this point. So what is the equation of the tangent plane? So the equation of the tangent plane is basically so the equation of the tangent plane not f of x comma y, let's say some z, which is, let's say, h of x comma y, which is nothing but f of a comma b, right, plus gradient of this function at a comma b dot product with x minus a y minus. Okay, so then this, whatever this function is, this this plane is, so now I am getting a plane, right? So del f times x minus a y minus b. This equation will give me the equation of the tangent plane of f at a comma b. Okay. So let's try to compute the equation of the tangent plane for the same function. Okay, so here we have computed the tangent line. Okay, let's try to compute the equation of the tangent. So for the tangent line, you have a direction. For tangent plane, you don't have any direction. Okay, so means direction in the sense I'm taking some kind of unit vector in the domain. Okay. So you don't have, because once you have all the tangent line, then basically yeah, so basically tangent plane contains all of your tangent lines under certain conditions. Suppose I want to compute the equation of the tangent plane of this function at, let's say, 1, 2, right? So for that, what I have to do, I have to compute the gradient first. And what is the gradient? It's 2x, this is 2, 2y, this is 4, right?
Yeah.
So then you just apply this thing. Okay, this is it. So, and one more thing you need just f of a comma. Okay. So f of 1, 2 is 1 square plus 5. Then you have gradient 2, 4, x minus 1, y minus 2.
2x minus 2.
Yeah, so y minus 2. And if I write this 5 plus 2x minus 2 plus 4y minus 8, then what I will get? 2x plus 4y minus 5. Okay, so then this is basically the equation of the tangent plane. Equation of the tangent plane. Yes. This is the best linear approximation of this function at point 1, 2.
Oh, linear approximation means tangent plane.
Yeah, tangent plane is basically the best linear approximation. So basically, what actually
not the tangent line.
No, not the tangent line. Tangent line is no, it's actually it's the best linear approximation along the direction of u. Okay. Along the direction of u, that you can say.
Direction, then it's tangent line.
Then it's tangent line. Okay, so see tangent line. See, the thing is, if you see this tangent line, it's more or less a line. You can say it's a function of one variable. Okay, you certainly using a function of one variable, you cannot approximate a function of two variable, right? So here you have a function of two variable. Right? So in some sense, when you have when actually you have a function of one variable, okay, then actually you have this tangent line, whatever you are getting, you say it's a function of one variable. So then in that case you have, then this is the best linear approximation of that function at the given point. Okay. But when you have a function of two variable, so basically you need a plane to approximate this function.
Right.
So when I'm talking about tangent line, okay, when I'm taking tangent line, it's basically approximation of this function, approximation along this direction, the best approximation of this function along this direction. Okay, so again, see the finding equation of tangent line and equation of tangent plane is more or less equivalent to finding the values of directional derivative and the value of the gradient. Okay, once you know how to compute the directional derivative and the gradient, then equation of tangent line and equation of tangent plane, they are basically just simple computation. Okay, so yeah.
How can we find the equation of tangent hyperplane for the same question?
What do you mean by equation of a tangent hyperplane?
We got it right now. Same question.
Sorry?
Same question only we got now, correct? Hyperplane.
Yeah, sir. So for same question, how we get the equation of tangent hyperplane? Sir, there's a difference, right?
Not difference. There is no difference. The tangent line is basically tangent plane is basically hyperplane here, right? This is a two-dimensional object, right? The plane is a
two-dimensional.
Sorry?
So this equation is also a hyperplane.
Yeah, this is a hyperplane, right? It's basically translation of a plane, right? And plane is a two-dimensional thing.
Okay, sir. Okay, sir.
In the definition of hyperplane, actually you need if you go to the proper definition of hyperplane, you need one extra condition that subspace has to be a vector subspace. Okay, so
okay, it has to pass through zero.
Yeah. But yeah, it's basically if you talk about the dimension as a affine space, this one, okay, then the dimension is 2.
Yes, so the whole dimension is 3. The dimension of the whole plane
are 3. Yeah, it's 3, and the dimension of this plane is 2. So that means it's a hyperplane, right?
Okay.
See,
so
the thing is, if you take the equation, if you find the equation of tangent, let's say some plane in for a function of three variable, for a function of three variable, then also you will get some hyperplane in R4. Okay, so that is how we define it. Okay, so then you will get a hyperplane in R4. If you define for, if you try to find a tangent plane a function of 5 variable, then you will get a hyperplane in R6. Okay.
Yes, sir. Yeah.
Yeah, so that is the tangent plane, by definition it's hyperplane. Okay, so
Okay, sir. So finding a hyperplane is same as finding the tangent plane. There is no difference between them. It's just a difference of the,
a tangent plane is a hyperplane, but you see the thing is, if you take any arbitrary hyperplane, then that may not be a tangent to this function, right? This may not be a tangent plane to this function at this point.
Okay, sir. Okay.
Tangent plane is a hyperplane. Okay,
Okay,
that is for sure. But if you take some arbitrary hyperplane, then that may be a tangent plane to some other function.
Yeah. Okay, sir. Okay. Thank you, sir.
Yeah, thank you. Okay, so yeah, so the thing is, yeah, okay, so
steepest ascent and descent, you will.
So critical points are there, right? In this chapter.
The steepest ascent and descent will come before that, right?
Okay, so yeah, so okay, that is basically it's okay, so that is the maximum, the rate in which direction the directional derivative is maximum, right?
Yeah.
Yeah, so yeah, so that is, yeah, so basically, yeah, so it's again, I guess you know that. Okay. Since you are asking that question, I guess you know that.
It is only the unit, sort of a unit gradient vector.
Yeah. So the thing is, yeah, so so the thing is, you compute the directional derivative of maybe say of some function. So you come, so let's say you have some point a comma b, and you are trying to compute the directional derivative in bunch of directions. So in direction. So we want to say among all the possible direction, in which direction the directional derivative is maximum. Okay. So
in the same direction only.
Not in, what you mean by in the same direction?
So I mean in the direction
of in the direction of
yeah.
gradient. So
yeah, gradient direction, yes.
Yeah. So it's basically the directional derivative is maximum when you are computing the directional derivative in the direction of gradient. Okay, but since we are always taking the unit vector, it's basically you have to take the modulus, okay, norm of that gradient vector, and it's basically its minimum
opposite direction.
Yes, when you will take the opposite direction.
When the unit vector is equal to the,
yeah, so when the unit vector equals to here this, and this is minimum when the unit vector is basically this. Okay, and if you compute the directional derivative of this function along this direction, I'm assuming that I can apply that gradient formula. Okay, so what you do, you compute, you take
modulus
AB dot
AB by the norm.
Norm, right?
Yeah.
So this is nothing but
Norm of Norm of the gradient.
This is basically normal. Right. So, so this is
that is the directional.
This is the maximum directional derivative. Okay, this is the maximum value of the directional derivative. Okay, since the maximum value of the see in this direction, it will give you the maximum directional derivative, and that value is basically this. Okay, and in this direction, it will give you the minimum directional derivative, right?
Yeah.
And that value is basically this. Okay. The negative of that. That's. I'll try to do some examples. Maybe I don't know whether I can do that, but I'll try to do it. So okay, so the next thing is critical points, right? So I'll come to that. Like Vishnamon, I'll try to solve few of your questions, but yeah. So again, like, see, the thing is, okay, so if you want to, that's why you should ask all these questions in your main session, or otherwise it will be slightly.
Sir, can I ask just a question, sir, about this maximum and minimum variation? So basically, we are getting quantum of variation and direction of variation, both, is it not?
Sorry, quantum. I don't know the word. Like, what do you mean by the quantum?
Magnitude of the variation and the direction of the variation?
No, basically, see, we are computing in which direction the directional derivative is maximum.
Yes.
And after that, we are computing the maximum value among maximum value of the directional derivative among all the possibilities.
Yeah, yeah. So maximum value also we are getting. So maximum value is given by your norm of gradient f at that point AB.
Sorry. Can you repeat?
Maximum value is given by that norm of the gradient at the point AB.
Yes. This is basically the maximum value. Yeah, correct. And
the minimum value is also given by that only.
Yeah. And this, yeah. So this maximum value is achieved along this direction. Okay, developed by this, and this is precisely the minimum value, and you can achieve that along this direction.
Okay.
This is the value of the slope, right? Slope. We can say equate to a slope.
Yes. It's basically the rate of change. Yeah, that is basically the slope. Yeah. True.
But sir, generally in derivation, when we can compute maxima, minima, when thing comes minus, it is maximum, and when the derivative, and when the derivative is positive, it is minimum. Is it not?
Sorry.
When the second derivative.
Yes, secondary. No. Here actually, if you go and check, like I guess Sir has done it in his lecture. Okay, if you see like the way actually we have defined this dot product. Okay, so if you go and check, yeah.
So here the sign is reverse of the traditional.
Yeah. So if you, as I said, if you go and check this definition, like I guess as far as I remember, Sir actually he has done all this calculation in the lecture. So yeah, true. Whatever you are saying, whatever observation you are saying, yeah, it's correct. Like in generally when you get negative, like if you go and check the second derivative test, when you get negative, generally you get
maximum.
Maximum, yeah. When you get positive, you get minimum.
Yeah.
But that is what you are getting here, right? When you are computing the maxima and minima of a function.
Okay.
That is also you are getting here, like, but this is a slightly different thing. Okay, when you are computing critical points, then you are doing basically this Hessian test. Then basically whatever you have done in your one variable calculus, more or less you are doing the same thing, but again you have some kind of mixed partial derivative, which is slightly annoying.
Okay. Thank you, sir.
Yeah.
Thank you.
Okay, so we have to. Okay, so let me. Okay, let me discuss critical points. So, so basically you have a function and Rn to R. So a point in your domain, it's said to be critical point of your function A if one of the two things, just like the case of partial, like one variable. So here you have, if the gradient is 0 at that point, if the gradient is 0 at that point, 0 vector, gradient is a vector, or you have one xi, or you have at least one xi for which the partial derivative at that point doesn't exist. Okay. So in that case, you can say that your then you can say that this point is a critical point of that. Okay. So so in that case, you can say that your point is a critical point. Clear? The definition is clear. Just like the same thing you have seen in the case of one variable, right? If the function, the derivative of the function is 0, or the derivative doesn't exist. So here in the case you don't have derivative, you are not using derivative. We are basically we're taking the partial derivative. Okay, so either all the partial derivative are 0, or one of them doesn't exist. In that case, you say that
if the partial derivative exists, but the partial derivatives are not continuous, then
no, then you don't need that. Okay, to talk about critical points. Okay, you don't need continuity assumption. Okay, if the partial derivative exists and 0, or if all the partial derivative exist and 0, then you say that is a critical point. If one of them doesn't exist, then doesn't exist, then also you can say that is a critical. Okay, you don't have to check about the continuity of the partial. Okay, so okay, so let me take some example. In most of the cases, you will see questions like when the function, when you will see question in this case. Okay, so in very few cases you will have some point where the partial derivative doesn't exist. Okay. Because in most of the cases you are going to deal with polynomials. Okay, in that case your partial derivative always exists and it's continuous also. But again, for critical points, you don't need that continuity. Okay, you just need the assumption. You need this condition. Either it's 0 or it doesn't exist. yeah, again, I'll come to all your question in the end. Okay, so let's say some question. Yeah, cos xy also you can take. It's not a big deal. Okay, let me take. So you just need to know the idea, like how. So I don't know whether this function, let's say x cube plus y cube minus 3x minus 3y. Okay, this is my function. Okay, so this will never occur for this function. You will always, the partial derivative always exist. Okay, so this will never occur for your function. So now, first thing you have to do, you have to compute f of x. What is f of x? 3x square
minus 3.
Minus 3. And you have f of y.
3y square minus 3.
So from here, what you are getting, you have to equate it 0. So what you will get? X equal to?
X equal to
plus minus 1.
Plus minus 1, right?
Yeah.
And what you will get from here?
Y is
Same.
Plus minus 1.
Y equal to plus minus
Plus
1.
minus 1.
Then how many critical points you have?
4.
4.
1, 1. 4,
So then
1.
you have 1 is 1, 1, 1, minus 1, minus 1, 1, minus 1. So then you have 4 critical. So
About the boundary points.
no, 4 critical points. 4 critical
Yes, sir.
points. Yeah. Yes. So you here you the domain of the function is R square. You don't have bounds.
Yes, sir.
Yeah. You basically you don't have bounds.
So to know whether these are maxima or minima, you have to go for second derivative check.
You have to go for the Hessian. Yeah.
Hessian or second order.
Yeah, Hessian is basically.
Oh yeah, Hessian matrix.
Hessian in Hessian matrix, actually you are
Second order, yeah.
yes, computing the second. Let me. Okay.
Here we can directly find the values. Right?
Sorry.
We can find the values of the f.
Yeah, but certainly by after putting the values of finding the values of f, you simply cannot say like whether that point is a point of maxima or minima, right? You simply you can know.
You cannot compare the result. It is
no, actually, it's sometimes you can have saddle point like, and you cannot say simply by substituting the values of the function in f. Okay. So so you basically you cannot say anything about it. Okay, whether it's a point.
How to find saddle points, because that is the main thing actually we always get
No,
confused.
that is what I'm going to do. Like basically I'm going to tell you some, that is what you do in week 11, right? So after finding Hessian matrix, you use some test, right?
Yeah, correct.
And from there you can say which one is saddle point, which one is point of maximum, point of minima, when your test is inconclusive. Okay, so I'll come to that. Okay. So once I introduce the Hessian, then I can talk about all these things. Otherwise, there is no point of this maxima and minimum, these things. Okay, so now I'm still with this critical point. Okay, I'm just showing you how you can compute the critical point. So in this case, this is how you compute the critical points. Okay, let's say suppose you take some x, y, don't know, 2x minus 2y plus 5 I want to compute the critical points of this function. Okay, I want to compute the critical points. Okay, so what is f of x? It's 2x plus y, right?
Plus 2.
Plus 2,
Plus 2.
correct. Plus 2, correct. And what is
X,
f of
x plus 2y minus 2.
Minus 2, right? Well, now it's pretty easy to find the critical points, right? Because this is a line. If you equate this to 0, this is also a line. And you need to find where they basically intersect. Okay, if they are parallel, then certainly they are not going to intersect. Then in that case, you don't have any critical points. If they are not parallel, then they'll intersect at a point. Okay, so okay, let me do it quickly. So this is 2x plus y minus 2x plus 2y equal to 2. You multiply 2 in both this here, then what you will get?
So x equal to minus 2.
X equal to minus 2. Once x equal to minus 2, y equal to 0.
Y equal to 2.
Y equal to 0, right? Huh?
Y equal to 2, sir.
No, if x, I don't know whether this is correct. If x is equal to minus 2,
X is not equal to minus 2.
Sir, minus 2 and 2. X equal to minus 2, y equal to 2.
X equal to?
Minus 2, y equal to 2.
No, if x equal to minus 2, then y cannot be 2.
Yeah, minus 2 means it will
Yes, y equal to 2, sir.
Y is 2.
Y is 2, sir. You solve
Y
it.
is 2, sir.
It will not be 0.
If y is 2, then x cannot be minus 2. That is my point. Okay, let me
X
take.
minus 2 will come,
Yes, sir.
it will become 4, sir. 2y will become 4.
Sir?
Okay. Plus 4. 2. And it's basically we are getting minus 1, right?
Minus 2, sir. 2 minus 4.
4,
Okay,
no?
sorry.
X equal to minus 2, y equal to 2.
Yeah, correct. Yeah. So then this is your critical. This is the only critical point of. Okay, so next let's go to Hessian.
So y is 2 by 3, sir.
Sorry?
X2, y2 is not a correct answer. Y is 2 by 3 and x is something else.
Okay, you compute. Okay. If this is not the correct answer. Okay.
No, it's not correct.
Yeah, it's you can compute. Okay. So how you define? Okay, like how you define Hessian?
Perfect 6.
It's basically what? Suppose you have a function of n variable. So basically this Hessian matrix, how you define? You take the gradient. Okay. You take the gradient. Right. In the first row, you take the first the derivative of the partial derivative of the gradient with respect to x1 variable. Okay. So then what you'll get here? In the second row,
D square F.
You take with respect to you take the gradient with respect to x2. Okay, partial derivative. Yeah. So
x2, x1. x2, x2.
And for the nth, you take with respect to right. This is how you define the Hessian matrix. And if you want to compute the Hessian matrix at some point A1, A2, AN, then basically you have to evaluate all these functions at this point. Then you compute all the component of that matrix. That is how you compute your Hessian matrix. Okay. Okay. So, so for a function of two variable, what will be the order of the Hessian matrix?
4.
4, right?
2 by 2.
So it's basically
2
order is basically 2. Okay, it's not 4. Sorry. X square.
So here we are first differentiating with respect to y, then we are differentiating with respect to x, right?
Yes, yes. Yeah. I'm taking gradient, then I'm first differentiating with respect to x, then in the first row, second row, I'm differentiating with respect to y. Dy square, right?
2, 1, 1, 2.
Sorry?
2, 1, 1, 2. The value will be.
Sorry?
The value will be 2, 1, 1, 2. The matrix.
What do you mean by 2? No, what? I am not computing anything, right? I'm just writing the.
Okay.
Okay, so so suppose I have a critical point of this function. Suppose a comma b is a critical point of this function, and I want to know whether that point is a maxima or minimum, right? So if okay, so it's certainly you don't have to remember anything. Okay, you can see like if this is greater than 0, okay, and the determinant of the matrix is greater than 0 at a comma b, then you have a what? Minimum, correct. If your, let's say, determinant of the Hessian matrix, so this is my Hessian matrix. First thing is you need this to be greater than 0. Same thing you have done, like more or less you have done for the case of one variable. So if this is greater than 0 and the determinant is greater than 0, then you have point of minimum. Okay. Now, what is the second condition?
If the d square f by dx square is less
so
than.
This is now this is actually this one is 1 cross 1, right? This is a 1 cross 1 matrix, and this is a 2 cross 2 matrix. So and the whole is 2 cross 2 matrix. For 1 cross 1, you have minus. Okay, if this one is less than 0, because this is a 1, so this is a 1 cross 1 submatrix of this whole matrix, and the second one is the whole matrix. This is 2 cross 2 matrix, so this is positive, then you have a point of maximum, right? And the second thing is if this is less than 0, then you have a saddle point. right? If the determinant is 0, then the test is inconclusive, right?
Yes.
So now let's say I have computed some 4 critical points, right? Let's say this is my function x cube y cube minus 3x minus 3y. X cube y cube minus 3x minus 3y. So what is the what is the Hessian matrix of this function? What is the Hessian matrix of this function?
6, if I'm not wrong.
So what you have to take? Del of f square of f dx square, right? This is the first thing. So the first thing is 3x square, then 6x, right?
Yeah, 6x.
Then you have to take the sorry.
Yeah. 6.
This you will get 0. Okay, if you take the second derivative here, you will get 0. Then you have to take the partial derivative. So
6x 0 0 6y.
Yes, 0 and 0, 6y.
You will get 0 0
6y.
Yeah.
6y.
Okay, so now I have 4 critical points for this function. One, yeah. So I have 4 critical points. I have to check one. Let's say let's check this at 1, 1. Okay, so at 1, 1, what is this thing? The matrix
6
0 0 6. So now you can say this is greater than 0, right? This is greater than 0, and the whole determinant is greater than 0, right? That means 1, 1 is a point of
minimum.
Yes. So the next one is 1, minus 1, right? What will be the thing? 6 0 0 minus 6. Now this is greater than 0, right? Here greater than 0, but the determinant of the Hessian matrix is less than 0, right?
Yeah.
So that means
saddle point.
Saddle point. Okay, by our condition, if this determinant is less than 0, I have a saddle. Okay, so
only finding determinant is sufficient, right, to find the saddle point? If it is less than 0, yeah.
Yeah, for 2 cross 2, I guess it's fine, but I don't think you can apply the same thing for 3 cross 3.
Okay.
For 2 cross 2, if determinant is less than 0, then you can do it. Yeah. Okay, so and I have minus 1, and similarly, if you compute at minus 1, what I will get? Minus 6 0 0 minus. And you can see this is less than 0, but the whole determinant
is
positive. Okay, so that means this is a point of maximum, right? If this is less than 0 and the determinant is greater than 0, then we have a point of maximum. I have taken all the Okay, another one is -1, 1, I guess, right?
Yeah, -1, 1.
Again, I guess for this you will get a saddle point.
Saddle point.
Yeah, because the determinant is basically less than 0. The determinant of the Hessian matrix. So then you have a saddle. Okay, so this is how you compute once you know once you compute the Hessian, and after that you need to apply this bunch of rules.
Sir, suppose determinant is greater than 0 and fx is equal to 0, then what we can conclude?
If determinant is
greater than 0 and differentiation with respect to x, the
0.
First element is a 0, yes, sir, of Hessian matrix.
No, you are saying this is 0.
Fxx is 0. Yes.
Yes, sir. Yes, sir. Let's suppose an what function I don't know, but a function for which we get a Hessian matrix just like a 0, -1, 1, and 1.
This is 0, right? This is 0.
Yes, sir.
See, if this is 0, okay, then basically see the thing is what actually you are doing. If this is 0, then either the determinant will be 0, okay, or the determinant will be negative.
No, sir, I can take -1 and a 1.
No, you cannot. Actually, see, the thing is, okay, so the thing is actually what will happen.
Partial difference is not continuous, then we can get a different thing for.
Yeah, for that case, actually, you need different thing. But I guess to apply this to apply this test, you need that condition. See, this test actually holds once the partial derivative is actually continuous.
Okay. If not continuous, then we can't apply this test.
Yeah, correct. Yes. So you need, so basically if you write actually what you will get, so in that case, so basically you will get some square term. Okay, you will get, so this is basically f of y minus f of xy square. So when I'm writing this, actually I'm assuming that this xy, they are same. Okay, so when you are saying this is 0, then you are actually so then this one is positive. It's always greater than equal to 0. So either the determinant is 0 or it's -1. Then it's or it's some negative number. In that case, either the test is inconclusive or it is a saddle point. So yeah. So the thing is, so if you go and check the lecture, actually, so you need that condition. Okay, so you have some kind of like the Clairaut's theorem, whatever you need this the partial derivative is continuous. Okay.
Okay, sir. Yes, sir.
Yeah.
Sir, I just had one doubt. Sir, this del f upon del x del y. So you first differentiate with respect to y or x?
Which one?
Sir, del f upon del x del y.
Del f upon
del x del y.
First you differentiate with respect to y, then with respect to x.
Okay.
Sir, due to Clairaut's theorem, the diagonal elements will always be the equal, right?
Yeah, because so the thing is, we can apply that test when actually we have when the Clairaut theorem holds.
So we don't have to calculate for every element; it will be the same. Like
no, you don't have to calculate. Like you don't have to calculate. It's basically you will get the same thing. Okay. If you change the order, it doesn't matter. Like you will get the same.
Here we calculate only which is the maximum minimum saddle point. We don't calculate the function values now.
You can after that you can substitute and compute the value, right? We just want to know the point of maxima and minimum. Okay. So if you want to compute okay, then you can substitute the value and you can get right. It's not big deal, like you can get. Then you have like similarly you can actually you have same thing for, let's say, for you have similar kind of test for a function of 3 variables. So so what is the what, like this Hessian matrix? This is f of x, right?
Yes, sir.
This is
Yx.
then
Yx.
yx, right?
Yes.
This is zx.
FZX.
And this one is
xy.
XY.
Y.
yy.
Yes. ZY.
This one is
XZ.
xz.
YZ, ZZ.
So again, like as I said, you don't have to remember anything. So this is a 1 cross 1 submatrix. This is a 2 cross 2 submatrix. This is a 3 cross. So the whole matrix is a 3 cross submatrix. So you are computing. So this is basically x, y, z. So when you compute the, so you want to check whether this is, suppose ABC is a critical point and you want to know whether this is a, then you want to know what is the behavior of function at this function, whether it's a point of maxima or minima or a saddle point or whatever the Hessian, whether we cannot conclude from the Hessian test, whether we cannot conclude anything from the Hessian test or not. So for that you need to apply bunch of rules. So the first rule is, again, for point of minima you need everything to be positive. This is positive, this is positive, this is positive. Okay, so the first thing is determinant of the first one, which is basically f of xx. This is unit positive, and the determinant of the second matrix, which is basically f of xx minus f of yy, and xy and yx, they are basically same. Sorry, you can write it as f of xy square greater than 0, and the final matrix determinant of the Hessian is 0. Then the next thing is for point of minima, maxima, this is the first thing. Okay, this is negative. This is a 2 cross 2 matrix. 2 is even, so this is positive. This is a 3 cross 3 matrix, so that is odd, that is negative. Okay, so again, you don't have to remember all these things. Okay, it's basically once you know for function of one variable, then you are done. So this is, if this is, that means ABC, say point of maximum, sorry, point of minimum. This is less than 0, right? This is greater than 0. And final determinant.
You see the matrix once.
Sorry?
Show the matrix once.
I can't hear you. Like, can you repeat?
Can you just scroll a bit above to see the matrix once?
Just a minute. Let me complete.
Okay.
So we don't have to remember this entire thing, sir.
Sorry?
We don't have to remember this entire part.
That is what I was explaining, right? You don't have to remember. So, so then in this case, you have a point of maximum. So as I said, this is your one case, one submatrix of your Hessian matrix. The only thing you have to remember is Hessian matrix, and that is also you don't have to remember if you remember grading. Okay, so yeah, that is the thing. That is, and saddle point is basically if your determinant is determinant of the this is non-zero, and your case 1 and case 2 don't occur. This one and this one don't occur. Then you say ABC is a saddle. And if determinant is 0, then you say your test is conclusive. Okay. Again, I'm certainly I'm not going to solve question for case of 3 variable. It's the same thing. You basically you have to compute the determinant, and you have to compute the matrix, and you have to compute like what sort of possibility at that point. Like you have to check which at that point which of the following is true. Okay, so is it clear? Like basically, at least I have done an example for the case of 2 variable, and similarly you can proceed for the case of 3.
Is there any application of this?
Sorry.
Any application? How?
No, the thing is, okay, so the finding actually, this finding maxima and minima actually it's really crucial. Okay, when actually you have some kind of problem, like let's say some optimization problem, right? So how actually you compute it? You have to optimize the function, right?
Yeah.
So then in that case, you need to find a point where the function attains its maxima, or let's say minima. Okay, so when you have cost, you want to minimize it. Okay, so then you have to search for a point of minimum. When you have profit, then you have to maximize it. So certainly maxima minima, it's see, finding maxima minima of function is it's crucial in almost each and every area of mathematics. Like so not mathematics, like mostly in the optimization thing. Okay, so
sir, yeah, here in case of these 3 variables, sir, for saddle point. So can I say the moment my second order determinant becomes negative, it is a saddle point, and of course determinant is not equal to 0. Third order determinant not equal to 0, right?
You are saying if your second order determinant is
negative, because it has to be positive in all the cases. So the moment it becomes negative and my third order determinant is not equal to 0, then immediately I can say it's my saddle point.
Yeah.
Yes. And the moment the third order determinant becomes 0, it's inconclusive.
Once this is 0, then
Then it is inconclusive. Okay, sir. Thank you.
Okay, so yeah, so that's all. Like yeah, so you don't mostly you need to find the critical points of maybe bunch of polymers. So
great, sir, you have covered the entire concept. Thanks a lot.
Yeah.
The whole credit goes to you, sir.
Okay.
One session you have covered all the 3 weeks.
Yeah, basically I have tried to recall all the things because I didn't solve much problems. So
you have solved significant number of problems, so just to relax.
Okay, but yeah, so the thing is most of them are like slightly
I think the only point which I think some of us or I am struggling still. I'm not able to understand why partial derivative or directional derivative exist when the function is not continuous at a particular point. So that concept is only not clear. It's fine, but the mechanism is
No.
clear.
That is what I'm saying, right? I have gave you some. See, the thing is, again, I'm saying so. So the thing is, when you have a function, let's say you have a function. Okay, when I'm saying the partial derivative
or directional derivative.
No, yeah. So when I'm taking directional derivative, okay. So I'm just taking the behavior of the function in this direction. Okay. I don't care what is going on in some other direction. I don't even care whether in this direction the limit exists or
Let's say we calculate at a particular point. Say for example, we calculate at 0, 0, right? So why we are not checking continuity at 0, 0? Because in differentiation generally we
no,
check
that is what I am saying, right? When you are checking continuity at 0, 0, what actually you are checking? When you are coming to 0, right?
From left side
from each and every possible direction you
right.
should get a unique limit, right?
Okay.
But when I'm computing the directional derivative in this direction I only care about this particular part. Okay, I don't know how this function behaves in here, right? It can be very, very bad here. Okay, the function behavior can be very bad. So maybe when I'm coming from this direction, the limit doesn't exist. Okay, so
suppose then it is clear for, say for example, it's fine with directional derivative. What about partial derivative with respect to x? Because in that case, I am approaching to 0 from x-axis only. So in that case, why don't we check continuity at 0, 0? Okay, for directional derivative, I got it. What we are trying to say.
No, partial derivative is basically it's a directional derivative, right? Partial derivative.
It's a special case of directional derivative.
So again, that will not ensure about the continuity of the function, right?
But one of the direction will be along the x-axis, that I am approaching.
No. Then one of the direction is x-axis, but again you have so many other directions, right? You don't know what is going on what is the behavior of the function in other direction, right? See the same thing. So when you are saying in the direction of x-axis, so then you just know what is going on in this direction, right? You know what is going on in this direction, but there are a bunch of directions which you are missing. Or to be more precise, you are still missing infinitely many directions. You don't know what is going on here.
But we say, sir, that even limit doesn't exist even for one direction. Then the entire limit does not exist. Like when we say x1, x2, x3.
That is the advantage. That is why the limit, the partial derivative is not if the partial derivative exists, then you cannot claim that your limit exists, because in partial derivative we are checking only for one direction. Okay, but when you are checking the limit, you are checking from all the possible directions.
All possible directions.
So when the partial derivative exists, okay, you know that in this direction the function is pretty nice. Okay, then you can say that okay, it's good. In this direction the function behaves nicely, but you are missing all this direction. Okay, so so maybe you have some path here. If you come to this point using some path here in this point, so where the limit doesn't exist.
Okay, sir, just as you told that partial derivative is a special case of directional derivative. Okay, so this concept is clear, sir, but just I'm trying to understand it intuitively. Let us take some real life example. Say for example, my body mass index is a variable of 2 parameters, my weight and my height, right? So when we say partial derivative, it literally means that I am keeping one parameter constant and I am playing with other parameter, right? So one unit change of other parameter, how is my function impacted? Is getting impacted, right, sir? Am I correct?
Okay, like no, the thing is, okay, you cannot take your body actually as a.
Okay, let us.
So the thing is, when you want to take your body as a function, you have to take the surface of your body. Okay, it's basically you cannot take your whole body. Okay, so that cannot be a function. Yeah, you have to take the surface of it.
Okay, let me redefine my question in other way, sir.
The thing is, okay, so the thing is, okay, so the thing is, it's nothing like that. It's basically you have a function and in some direction it's telling you how. See, the thing is, when you are taking your single variable thing. So when you are computing the derivative, it's giving you the slope, right? So the same thing happens in the case of one variable. Okay, so sorry, two variable.
In case of two variable, when we talk about,
It will give you the slope of the tangent line. Okay, it will give you the slope of the tangent line. That is how you define tangent line, right? So when you have this point and you have some u1 here, okay, so you have some u vector here. When you are taking the directional derivative of this function at point, let's say this, then basically this slope of this line is basically your directional derivative. Okay, this is basically the slope of this tangent line. Because you are basically taking a line in the direction of u, like you are up, it's the same thing. Whatever you are doing in the case of one variable, you are doing the same thing here. But basically, because when I'm taking actually in particular direction, then basically I'm treating it as a function of one variable. So in some sense, I'm doing the derivative, the same derivative, whatever I have done in the case of one variable, I'm doing the same thing here by treating this function as a function of one variable.
Sir, this mock, enter mock, the answers are there. Any how to solve? You will post something like that, or
no? We have posted yesterday.
Really?
Yeah, solution we have posted, right?
Solutions are there, which is correct answer is there, but how to solve is
no. The whole calculation we have posted.
Which I could find it.
No, it's there, right?
Be in the supplementary or
just a minute.
Oh yes, sir, it's there too.
Where?
It's under the same section.
Yeah. Yes.
Got it, right?
Yes.
I have a doubt in that mock solution. About question number 6, affine mapping. Can you
check the solution?
Yeah, I've checked the solution.
Yeah.
I understand the part where you are getting a linear transformation.
Yeah. Just a minute. Let me open it. Yeah. Okay. Mock for intern. Okay, let me share it. This mock paper is visible, right?
Right.
Yeah. So you have doubt in question number?
Question number 6 about that affine mapping. Yeah. So I got where you're getting the linear transformation, but I didn't understand how you're obtaining that affine mapping to take the vector from A1.
Yeah. So the first, yeah. So you got okay. So let me do it completely. So, okay. So yeah. Yeah. So can you just quickly tell me the question? So what is your A1?
2x1.
Okay, it's given. Okay, so A1 is basically it's basically the solution space of this C. So
do we have to find the solution space there?
No, you don't have to. You can do it even without doing that. Okay, so just tell me the matrix, like how A1, how we defined A1. So this, okay, the thing is I can go and check, but I have to do it a lot of times. 1 0 1 1 0 1 0 1 1 0 1 1. The next one is 1 minus 1 0 1 minus 1 0. This is 2 to 0. And we have this one. So the rank is basically of this matrix is 2. So then nullity is basically 1. So yeah. So it's a affine space of dimension 1. You can say 1 0 1
2 0 2 0 3
2 0 2 0 3. Its rank is 1. So it's a dimension 2, like affine space of dimension 2a2 2 4 6. So the thing is, it's given question number 6, it's given yeah, so it's -1 0 is the matrix representation,
right,
with respect to the ordered basis. Let's say 1 0 minus 1
1 and 0 1 0
1 0 minus 1 0 1
0 in the domain,
and then the codomain
1 1 minus 1
1 1 minus 1 1 1 minus 1. So then from here you are computing the linear transformation, right? You have computed it.
right. Yeah, I got T of XYZ is equal to minus x x.
XYZ equal to minus x
Minus x.
minus x. Correct? This is what you got, right?
Yeah.
Okay, just let me check whether your answer is correct or not. Otherwise, I have to compute it.
Yes, correct. In the solution, it is mentioned so.
Yeah. So then it's fine. So now, see, the thing is, for a single linear transformation, you can have multiple affine map. Okay, so you can have multiple affine map which correspond to the same linear transformation. So how actually you define plus some v1 and some e1. So now you have to check whether this v1, so T is a map from where to where? T is map from A2 to A1 or A1 to A2? Question number 6. T is a map from A2 to A1. Okay. So T is a map from A2 to A1. So this A2 is basically what? It's basically V1, this U2, this is V2, this is V1. So T is a map from A2 to A1. So A2 is basically U.
So excuse me, can you explain me how you got this T of XYZ? I didn't get this part. What is a T of XYZ plus V2?
So that is how you define affine map, right? What is actually affine map? How you get affine map? See, T is a map from what? U2 to U1, right?
Yeah.
but you want a map from where? A2 to
A1.
A1. But you know some relation. There is some relation between U2 and A2, right?
Okay, yeah.
U2, some vector V2 is basically A2.
Okay.
So once I replace here, once I add once I add V2 here, then basically what? I'm getting an element of
A1.
A2.
Right, A2, correct.
Yeah. So T of X comma Y comma Z is an element of what? U1, right? Because T is a map from U2 to U1. Okay. But I want a map. I want a map from T of A2 to A1. Okay. So once I add, so again I have a relation between U1 and A1, right? U1 is basically A1 plus V1, right? So once I add some vector V1 here, then I will get an element in A1, right? Right?
Yeah.
So then basically, see, the thing is, if you take any arbitrary element V1 in A1, okay, then this will work. If you take any arbitrary element V2 in A2, then also it will work. Sorry, not this U2, this is in A2, then this will work. So then basically you have to check option by option which actually is true. So if you see the first option, what is the first option? It's basically 2 plus x y minus x. It's basically 2 minus x.
2 plus x, x.
2 plus x, x, right? So 2, 1 minus x, x. So then this cannot be true, right? Because so here if you check the linear transformation is different, right? You are getting minus x, x, right? Correct?
So where plus one come?
Sorry?
So 2, 2, 1.
Which one? 2, 2, no, this is given, right? In the option 1.
Okay. So
Option 1, it's given, right? So here actually the thing is, here the linear transformation is different, right? Whatever linear transformation you are getting, this, let's say x, y, z, is basically minus x, x, right? So it's different. So here you are saying my linear transformation is minus x, x. So then certainly this map cannot correspond to this linear transformation. Okay. This map, whatever map this map is here, it cannot correspond to that linear transformation. Okay. So then you have to come to option 2.
F of 2 plus x, y minus x.
F of 2 plus x, y
minus x
is
equal to 2 plus x, 2 plus x, x.
2 plus x, 2 plus x, x. And again, this map, whatever this map, this is also, this is not the map which corresponds to this linear transformation, right? Because what you are getting here, 2, 0
plus x, x.
Right. So here the linear transformation, what are this linear transformation? So it's different, right? From the linear transformation that you got. Okay. So this may be a affine map, but certainly this map doesn't correspond to this given linear transformation. Okay. So this cannot be a correct answer. Okay. Then what about the third one?
What do an f of 2 plus x, y negative x?
Sorry, f of 2 plus y
negative x equal to 2 minus x, 2 minus x, x.
Sorry, 2 plus y minus x, then
f of 2 plus x, y minus
just
x.
a minute, let me okay. The third option is basically 2 plus x,
No, 2
y,
yeah, 2 plus x, y minus x.
2 plus x, y minus x. This one is 2 minus x, 2 minus x, x, 2 minus x, 2 minus x, x. This is
2 minus
2, 0
minus x plus minus x minus x x
minus x minus x
x. Yeah.
x.
Yeah. So that's a required linear transformation.
So this is now, what is this? This is 2, 0, 0 plus x, y minus x, right? So now, certainly this map, whatever this linear transformation, this certainly this correspond, this whatever this affine map is, whatever this affine map is, certainly this map correspond to the linear, to this linear transformation. Okay, right? But we have to check whether this is a map, truly this is a map from A2 to A1 or not. Okay, for that, what you have to check whether this is a element of A2 or not, and whether this is a element of A1 or not. Okay. So once you know, okay, this is a element of A2 and this is a element of A1, then you are done. Then basically this is a affine map from A2 to A. And basically you have to do for all the options.
So from the options we are arriving at the answer.
Yes, because there is no unique answer. Okay, you can have multiple answer. Okay, you can have multiple. See, the thing is, if I choose a different vector instead of some vector u1 and v1, if I take some different vector, okay, then I may get a different map, right?
Yeah.
So basically you have to check one by one. Okay, then only you can say. So simply by looking at the linear transformation, you can remove some of the option. Okay, if see once you know that this is my linear transformation, then simply you can say, okay, certainly option 1 and option 2, they cannot be correct because they correspond to a different linear transformation. Then you have maybe say, so here actually it's pretty clear from the if by simply by looking at the option, you can say, okay, this option 3 is, because that is the only linear transformation which basically correspond to the linear transformation correspond to option 3 is basically this, whatever you have calculated, this one. Okay. Okay. Okay, then I'll stop the session. Okay, thank you,
sir. Thank you very much, sir.
Yeah,
Thank you, sir.
Thank
Thank you for the session, sir.
Yes. Okay, again, we are not going to announce the weightage. So
Sir, is the end term will be similar to the mock?
yeah, you can not like not similar, but the level of the question will be similar. Okay, so some part will be similar, but yeah, not all.
Okay.
Mock was more inclined towards service space, affine service space and all.
Okay, like that you can guess. I don't have to. Whatever guess you want to do, you can do. Okay, I cannot tell anything in the
This
live
kind
session.
of inclination should not happen. That's what I. Too much inclination towards affine service space.
Okay.
Okay, sir. Thank you, sir. Thanks, sir.
Okay. All the best for your exam. Yeah.
Thank you, sir.
Yeah.